Imagine a cosmic speed limit so strict that nothing in the universe, no star, no signal, no flash of energy AI is allowed to break it. 300,000 kilometers per second. Albert Einstein called it the absolute boundary of reality, the master tempo of spacetime. But deep within the microscopic dark, in the strange, silent realm of quantum physics, two distant particles whisper to each other across trillions of miles instantly, defying the tick of time itself. Tonight, we step past the edge of classical physics to confront one of the most mind-bending questions in science. Is there something in our universe actually faster than light? Welcome back to the Dozing Dr. A, your sanctuary at the edge of the known cosmos. Here, we blend deep physics, astronomical mysteries, and theoretical science into immersive explorations designed to quiet an overactive mind and guide you into deep relaxation. Tonight, as you dim your lights, put on your headphones, and settle into bed, we step into a cosmic puzzle that baffled the greatest minds in history. Let the heavy rushing of your day slip away. Close your eyes, breathe slowly, and let us drift together into the interconnected, silent web of reality. When we look up at the night sky from a quiet place on Earth, space appears to be a vast, motionless cathedral. We see stars that seem to stand permanently in place, casting a soft, unwavering glow across billions of miles of absolute dark. To our everyday human senses, light feels instantaneous. When you flip a switch in a darkened room, the space is illuminated in a single, undivided moment. There is no visible delay, no perceptible motion of illumination traveling from the bulb to the walls. It feels as though light does not travel at all. It simply exists everywhere all at once. For thousands of years, ancient thinkers believed that light was indeed infinite and instantaneous. Philosophers like Aristotle argued that light was not a physical substance in motion, but a state of presence, a condition that simply was, without requiring time to cross distance. It was an intuitive conclusion born from the limitations of human perception. In our terrestrial lives, distances are so small that the time it takes for light to cross a room, a city, or even an ocean is far too brief for a human eye to register. Yet hidden beneath this illusion of instant illumination lies a physical truth that is far more breathtaking. Light is not instantaneous. Light moves. It travels across the dark as a continuous, rhythmic wave of electromagnetic energy, covering distance with a very specific, absolute velocity. In the vacuum of deep space, light moves at precisely 299,792,458 meters per second, roughly 300,000 kilometers every single second, or 186,000 miles per second. To put that staggering number into perspective, a single pulse of light could circle the entire globe of the Earth more than 7 times in the span of a single heartbeat. It can cross the 384,000 kilometers separating the Earth from the Moon in just over 1 second. When you look up at the Moon on a clear night, you are not seeing the Moon as it exists right now in this exact millisecond. You are seeing the Moon as it was 1.3 seconds ago. The photons of sunlight that reflected off those ancient gray craters had to travel across the freezing gulf of space, taking a full second and a third to reach your eyes. You are literally peering backward through the fabric of time. When you turn your gaze toward the sun shining as a brilliant golden hearth in our sky, the delay becomes even more profound. The sun rests roughly 93 million miles away from Earth. Light leaving the boiling, thermonuclear surface of the sun takes approximately 8 minutes and 20 seconds to slice through the dark vacuum and reach our atmosphere. If the sun were to suddenly vanish in a single, silent moment, Earth would remain bathed in warm, golden daylight for over 8 minutes. We would continue to orbit an invisible gravitational point, completely unaware that our stellar anchor was gone, until that final wave of light arrived on our doorstep. The further we look out into the cosmos, the deeper back into history we gaze. Sunlight reflecting off the swirling, cloud-banded surface of Jupiter takes over 40 minutes to reach our viewports. Light from Saturn takes over an hour. When we point our telescopes toward Proxima Centauri A, nearest star to our solar system A, are looking at light that left its surface more than 4 years ago. The distant, shimmering stars of the Milky Way galaxy are seen as they existed centuries or millennia ago, and the light from the Andromeda galaxy has been traveling across the intergalactic abyss for 2.5 million years before finally coming to rest against your retina. The night sky is not a photograph of the present. It is a layered, three-dimensional museum of the cosmic past. To truly appreciate why this speed limit exists, we must first ask a deceptively simple question. What is light? For centuries, physics was torn between two competing visions of light. One school of thought, championed by Sir Isaac Newton, held that light was composed of tiny, discrete physical particles called corpuscles, shot out from a luminous source like microscopic cannonballs. Another school of thought argued that light was a wave, rippling through an invisible, subtle medium that filled all of space, much like sound waves ripple through the air or water waves ripple across an ocean. It was not until the 19th century that a brilliant Scottish physicist named James Clerk Maxwell united electricity and magnetism into a single, elegant mathematical framework. Maxwell demonstrated that an electric field changing in time creates a magnetic field, and a changing magnetic field in turn creates an electric field. Imagine an electric field oscillating up and down in empty space. As it moves, its changing strength generates a magnetic field oscillating side to side at a right angle to it. That magnetic field, as it changes, regenerates the electric field ahead of it. The two fields feed off one another in a continuous, self-sustaining quantum embrace, dancing across the vacuum without requiring any physical material to carry them. This self-sustaining electromagnetic wave is light. When Maxwell calculated the theoretical speed at which these electromagnetic waves must travel through empty space using fundamental constants of electricity and magnetism, a single, exact number emerged from the equations: 300,000 kilometers per second. It was an astonishing revelation. Maxwell realized that light was not a separate entity from electricity and magnetism. Light was the physical manifestation of electromagnetic waves propagating through spacetime. However, Maxwell's discovery created a profound paradox that threatened to shatter the very foundations of physics. In classical mechanics, speed is always relative. If you are sitting inside a train moving forward at 60 miles per hour and you toss a ball forward at 10 miles per hour, an observer standing still on the ground outside watches that ball move at 70 miles per hour. Speeds add together smoothly and intuitively. For decades, physicists assumed that light must follow the same rules of relative motion. They reasoned that if light was a wave, it must be traveling through a universal, motionless background medium, a ghostly, invisible substance filling all of space known as the luminiferous ether. If the ether existed, then as the Earth orbited the Sun, moving through this stationary ocean of ether, we should measure different speeds of light depending on whether we were moving toward a star or away from it. In 1887, two American physicists, Albert Michelson and Edward Morley, constructed an exquisitely sensitive instrument called an interferometer to measure this ether wind. They split a beam of light, sending one half in the direction of Earth's orbital motion and the other half at a right angle, expecting to see a subtle shift in the speed of light as the two beams recombined. The result of the experiment sent shockwaves through the scientific world. There was no shift. No matter which way the Earth moved, no matter the season, and no matter the direction of the light beam, the speed of light remained precisely the same. The ether did not exist. Light did not obey the intuitive addition of velocities. Imagine standing on a platform as a spacecraft races past you at half the speed of light. If that spacecraft turns on a headlamp, shooting a beam of light forward, classical intuition says that you should see the light moving at 1.5 times the speed of light. But you do not. You measure the light from the headlamp moving at exactly 300,000 kilometers per second. And stranger still, the astronaut sitting inside the moving spacecraft also measures that very same beam moving away from them at exactly 300,000 kilometers per second. How could two observers, moving at vastly different speeds relative to one another, measure the exact same speed for the very same beam of light? It was Albert Einstein who had the courage to accept this paradox as an absolute law of nature. In 1905, through his special theory of relativity, Einstein proposed a radical rethinking of space and time. He stated that the speed of light in a vacuum is not just a property of light, it is a universal constant, identical for all observers regardless of their motion. To keep the speed of light constant for everyone, space and time themselves could no longer be rigid and absolute. They had to become flexible, dynamic, and elastic. If you travel faster through space, time must slow down for you relative to a stationary observer, a phenomenon known as time dilation. Distances must contract along your line of motion, known as length contraction. Space and time adjust themselves smoothly and precisely so that whenever you measure the speed of light, the ratio of distance traveled to time elapsed always equals the exact value of c. The letter c, used throughout physics to denote the speed of light, originates from the Latin word celeritas, meaning swiftness or speed. But as theoretical physics advanced throughout the 20th century, scientists realized that calling c, the speed of light, is actually a historical misnomer. Light travels at c simply because light has no mass. Any particle that possesses zero invariant mass, whether it is a photon of light, a gluon that binds quarks together, or a gravitational wave rippling through spacetime, is fundamentally obligated to travel through a vacuum at the speed of c. The value c is not merely a speed limit for light, it is the speed of causality. To understand why c is the speed of causality, imagine the universe as a vast, interconnected network of events. Cause must always precede effect. If you drop a glass onto a hard floor, the falling of the glass is the cause, and the shattering of the glass is the effect. The cause must happen first, followed by a delay as information travels through space, resulting in the effect. The value c represents the absolute maximum speed at which information, influence, or cause can travel from one point in the universe to another. It is the fundamental gear ratio of space and time. If an event occurs at a specific point in space, a star, exploding in a distant galaxy, gravitational, electromagnetic, and physical influence of that explosion propagates outward like an expanding sphere. This expanding boundary is called a light cone. Nothing outside that expanding light cone can feel, know, or be affected by the explosion until the boundary of c reaches them. If it were possible for a signal, an object, or a piece of information to travel faster than c, the strict ordering of cause and effect would crumble. Under the mathematics of special relativity, traveling faster than c in space is mathematically equivalent to traveling backward in time. If you could send a signal faster than light, there would exist frames of reference in the universe where an observer would see the effect happen before the cause. You could receive a reply to a message before you ever sent it. You could see the glass shatter on the floor before it ever fell from your hand. The universe enforces c as an unbreakable boundary to protect its own logical consistency. The cosmic speed limit ensures that reality remains orderly, predictable, and free from temporal paradoxes. It is the master tempo that keeps the past safely behind us, the present anchored in our awareness, and the future open before us. As a massive object attempts to accelerate toward the speed of light, another fundamental barrier arises: the relationship between mass, energy, and momentum. According to Einstein's famous equation, E equals mc. 2. Mass and energy are two forms of the exact same underlying currency. Mass is simply highly concentrated, trapped energy. When you push an object a stone, an automobile, or a spacecraft make it move faster, you are adding kinetic energy to it. At everyday speeds, this added energy simply increases the object's velocity in a straight, linear fashion. But as the object's speed begins to approach a significant fraction of c, something extraordinary happens. The energy you pump into the object to accelerate it no longer goes purely into increasing its speed. Instead, that added kinetic energy begins to contribute to the object's relativistic momentum, effectively making it heavier and harder to accelerate. As the object reaches 90% of the speed of light, its effective mass increases dramatically. To push it just a little bit faster requires vastly more energy. At 99% of c, the energy required becomes immense. At 99.999% of c, the energy needed to gain another fraction of a second approaches astronomical proportions. To accelerate a physical object with invariant mass, even a single microscopic electron the exact speed of c, you would require an infinite amount of energy. And because there is not an infinite amount of energy in the entire observable universe, no object that possesses mass can ever reach, let alone exceed, the speed of light. Only massless entities like photons can travel at c, and they can only travel at c. A photon cannot slow down, rest, or pause in a vacuum. From the moment it is born in the core of a star to the moment it is absorbed by an atom, a photon exists purely at the speed of c. And here lies perhaps the most mesmerizing consequence of the cosmic speed limit, the experience of a photon itself. Because time slows down as an object approaches c, a clock traveling closer and closer to the speed of light ticks progressively slower relative to the outside world. If a spacecraft could reach 99.9% of c, a journey that takes years from the perspective of observers on Earth would feel like mere days to the astronauts inside. At the exact speed of c, time dilation reaches an extreme infinite limit. Time stops completely. For a photon born in the heart of a distant star 10 billion light-years away, there is no passage of time. From the photon's own frame of reference, the moment it is emitted from the star and the moment it strikes your eye on Earth occur in the exact same, undivided instant. It does not experience the 10 billion years of traveling across the dark intergalactic void. To a beam of light, distance contracts to zero and time ceases to flow. The entire universe, across its vast billions of light-years, is experienced by a photon as an eternal, instantaneous present. As you float here in the quiet dark, listening to the rhythmic breathing of your own body, allow the profound elegance of this cosmic design to settle into your mind. The speed limit of the universe is not a wall built to confine us. It is a sanctuary built to protect reality. It ensures that light moves with disciplined, perfect harmony across the void. It weaves the tapestry of space and time into a stable, enduring fabric where stars can burn peacefully for billions of years, where planets can trace quiet, predictable orbits, and where living, conscious minds can rest safely, cradled in the unyielding logic of cause and effect. In the physical world around us, the cosmic clock ticks with unhurried mathematical perfection. The photons are racing across the deep voids, carrying the light of ancient suns toward distant horizons. Space is holding its boundaries. Time is preserving its sequence. And as we prepare to look deeper into the subatomic world in the chapters ahead, where particles seem to challenge these very boundaries, you can rest completely, safe in the knowledge that the ultimate speed limit of reality holds firm, keeping the cosmos in perfect, beautiful balance. As the gentle rhythm of your breathing slows and your body settles deeper into rest, let your awareness expand once more into the quiet realm of fundamental physics. In our first chapter, we explored the absolute speed limit of the cosmos, constant c$, 300,000 kilometers per second, the unbreakable gear ratio of causality. Now, we must take a step further into the mystery. We must ask, Why does this speed limit exist, and what does it do to the very world we inhabit? To answer this, we must unravel one of the greatest intellectual breakthroughs in human history, Albert Einstein's 1905 theory of special relativity, and witness how it tore down our ancient, intuitive notions of space and time, reweaving them into a single, dynamic continuum, the fabric of spacetime. To understand the world before Einstein, we must travel back to a time when space and time were viewed as rigid, unyielding, and forever separate. For centuries, human understanding of physical reality was anchored by the classical mechanics of Sir Isaac Newton. Newton envisioned the universe as a grand mechanical stage. Space, in Newton's view, was absolute an infinitely large, transparent, stationary box inside which stars, planets, and human beings moved. It existed independently of anything contained within it. Whether the universe was entirely empty or packed with billions of galaxies, absolute space remained unchanged, immovable, and eternal. Parallel to this absolute space was Newton's concept of absolute time. Newton wrote that absolute, true, and mathematical time flows equably of itself, without relation to anything external. In this worldview, there existed a single, master cosmic clock ticking away at the exact same rate everywhere in the universe. A second on Earth was identical to a second on the surface of the Sun, or at the farthest edge of the cosmos. Now had an absolute, universal meaning. If two events happened at the exact same instant aeon on Earth, and one in the Andromeda Galaxy were simultaneously present in the eyes of the universe, regardless of who was watching or how fast they were moving. This Newtonian model felt intuitively correct because it mirrors our daily, low-speed experience on Earth. When you sit quietly in a room, reading or resting, you feel motionless. The walls appear solid and stationary. Time seems to tick with steady, comforting predictability. Yet, long before Einstein, the Italian astronomer Galileo Galilei had already exposed a subtle flaw in our perception of rest and motion. Galileo invited us to imagine being inside a large ship below decks, in a room without windows. If the ship is docked quietly at the harbor and you drop a stone from your hand to the floor, it falls in a straight line. If you pour water from a pitcher into a glass, it falls straight down. Now, imagine that same ship smoothly sailing across calm seas at a constant, steady speed without pitching or rolling. If you drop the stone inside the windowless cabin, where does it land? It lands in the exact same spot on the floor beneath your hand. If you pour water into a glass, it flows straight down into the cup without spilling. No experiment you can perform inside that closed room can tell you whether the ship is sitting still at the pier or gliding silently across the open ocean at 50 knots. This is the principle of Galilean relativity. All uniform, unaccelerated motion is relative. There is no physical experiment involving the movement of solid objects that can distinguish absolute motion from absolute rest. Motion is only meaningful when measured relative to something else. When you sit in a chair on Earth, you feel at rest, but relative to the Sun, you are hurtling through space at 30 kilometers per second. Relative to the center of the Milky Way, you are sweeping around the galactic core at over 200 kilometers per second. For centuries, physicists accepted Galilean relativity for mechanical objects like cannonballs, falling stones, and sailing ships. But when James Clerk Maxwell published his equations of electromagnetism in the late 19th century, a deep contradiction emerged. Maxwell's equations demonstrated that light is an electromagnetic wave traveling at a fixed speed, see $. But a critical question remained. Fixed relative to what? If you run toward a sound wave traveling through the air, you measure the sound wave moving toward you faster than if you stood still. Sound travels relative to the medium of air. Physicists assumed light must behave the same way that it must travel relative to an invisible background medium called the luminiferous ether. If the ether existed, then Newton's absolute space was saved. Absolute rest meant being stationary relative to the ether. However, as we saw in Chapter 1, the famous Michelson-Morley experiment of 1887 shattered the concept of the ether. No matter how the Earth moved through space, light was always measured traveling at precisely $. Physics was plunged into a crisis. If Maxwell was right, the speed of light was constant. But if Newton and Galileo were right, speeds should add together, and light's speed should change depending on the observer's motion. The two greatest pillars of physics were on a direct collision course. To understand the world before Einstein, we must travel back to a time when space and time were viewed as rigid, unyielding, and forever separate. For centuries, human understanding of physical reality was anchored by the classical mechanics of Sir Isaac Newton. Newton envisioned the universe as a grand mechanical stage. Space, in Newton's view, was absolute an infinitely large, transparent, stationary box inside which stars, planets, and human beings moved. It existed independently of anything contained within it. Whether the universe was entirely empty or packed with billions of galaxies, absolute space remained unchanged, immovable, and eternal. Parallel to this absolute space was Newton's concept of absolute time. Newton wrote that absolute, true, and mathematical time flows equably of itself, without relation to anything external. In this worldview, there existed a single, master cosmic clock ticking away at the exact same rate everywhere in the universe. A second on Earth was identical to a second on the surface of the Sun, or at the farthest edge of the cosmos. Now had an absolute, universal meaning. If two events happened at the exact same instant aeon on Earth and one in the Andromeda galaxy Aethy were simultaneously present in the eyes of the universe, regardless of who was watching or how fast they were moving. This Newtonian model felt intuitively correct because it mirrors our daily, low-speed experience on Earth. When you sit quietly in a room, reading or resting, you feel motionless. The walls appear solid and stationary. Time seems to tick with steady, comforting predictability. Yet, long before Einstein, the Italian astronomer Galileo Galilei had already exposed a subtle flaw in our perception of rest and motion. Galileo invited us to imagine being inside a large ship below decks, in a room without windows. If the ship is docked quietly at the harbor and you drop a stone from your hand to the floor, it falls in a straight line. If you pour water from a pitcher into a glass, it falls straight down now. Imagine that same ship smoothly sailing across calm seas at a constant, steady speed, without pitching or rolling. If you drop the stone inside the windowless cabin, where does it land? It lands in the exact same spot on the floor beneath your hand. If you pour water into a glass, it flows straight down into the cup without spilling. No experiment you can perform inside that closed room can tell you whether the ship is sitting still at the pier or gliding silently across the open ocean at 50 knots. This is the principle of Galilean relativity. All uniform, unaccelerated motion is relative. There is no physical experiment involving the movement of solid objects that can distinguish absolute motion from absolute rest. Motion is only meaningful when measured relative to something else. When you sit in a chair on Earth, you feel at rest, but relative to the Sun, you are hurtling through space at 30 kilometers per second. Relative to the center of the Milky Way, you are sweeping around the galactic core at over 200 kilometers per second. For centuries, physicists accepted Galilean relativity for mechanical objects like cannonballs, falling stones, and sailing ships. But when James Clerk Maxwell published his equations of electromagnetism in the late 19th century, a deep contradiction emerged. Maxwell's equations demonstrated that light is an electromagnetic wave traveling at a fixed speed, c $. But a critical question remained. Fixed relative to what? If you run toward a sound wave traveling through the air, you measure the sound wave moving toward you faster than if you stood still. Sound travels relative to the medium of air. Physicists assumed light must behave the same way that it must travel relative to an invisible background medium called the luminiferous ether. If the ether existed, then Newton's absolute space was saved. Absolute rest meant being stationary relative to the ether. However, as we saw in Chapter 1, the famous Michelson-Morley experiment of 1887 shattered the concept of the ether. No matter how the Earth moved through space, Light was always measured traveling at precisely c dollar. Physics was plunged into a crisis. If Maxwell was right, the speed of light was constant. But if Newton and Galileo were right, speeds should add together, and light's speed should change depending on the observer's motion. The two greatest pillars of physics were on a direct collision course. Section 2. The Patent Office in Bern and the Light Beam. To visualize how time itself is forced to slow down, let us build a thought experiment in our mind. The light clock. Imagine a light clock composed of two highly polished parallel mirrors facing each other, separated by a distance of 1 meter. A single particle of light a photon A bounces endlessly up and down between the mirrors. Each time the photon strikes the bottom mirror, the clock makes a soft, rhythmic tick. Because the distance between the mirrors is fixed at 1 meter, and the photon travels at the constant speed c dollar, the time it takes for the photon to travel from the bottom mirror to the top mirror and back again is a fixed, precise duration. For an observer sitting right beside this light clock at rest, the photon travels in a straight vertical line. Up, down, tick. Up, down, tick. Now, imagine this light clock is mounted inside a futuristic, sleek train gliding silently along a smooth magnetic track at a significant fraction of the speed of light. You are sitting inside the train, traveling along with the light clock. From your perspective inside the train, nothing unusual happens. The two mirrors are stationary relative to you. The photon travels straight up and down between the mirrors, covering a vertical distance of 2 meters per cycle. The clock ticks at its normal, steady rate. Now picture an observer standing outside on the station platform as the train roars past at high speed. What does the observer on the platform see when they look through the train's glass window at the light clock? Because the train is moving horizontally, while the photon is traveling between the mirrors, the photon does not simply travel straight up and down relative to the platform. As the photon leaves the bottom mirror and heads upward, the top mirror is moving forward with the train. To hit the top mirror, the photon must travel along a diagonal path. Then, as it reflects back down toward the bottom mirror has also moved further forward, forcing the photon to travel along a second diagonal path. To the observer on the platform, the path of the photon forms an inverted V shape. This simple geometric difference changes everything. The length of a diagonal line is always longer than the length of a straight vertical line. Therefore, from the perspective of the platform observer, the photon inside the moving train must travel a significantly longer distance to complete a single tick of the clock. In Newton-Ayle's universe, this would be simple. The photon would simply move faster along the diagonal to cover the extra distance in the same time. But in Einstein-Ayle's universe, the second postulate holds firm. The photon cannot move faster than c dollar. The speed of the photon is fixed for both observers. Now let us revisit our equation, $backslash text time, backslash frac backslash text distance backslash text speed $. For the observer on the platform, the photon's path is longer, greater distance, but its speed remains fixed at c dollar, constant speed. The inescapable mathematical conclusion is that more time must elapse between each tick of the moving light clock for the platform observer. To the person standing on the platform, the clock inside the moving train is ticking slower than an identical clock resting on the platform beside them. And because every physical process in nature is mechanical ticking of a wristwatch, the firing of neurons in a human brain, the vibration of cesium atoms, the decay of radioactive isotopes is ultimately governed by electromagnetic interactions traveling at the speed of light, everything inside the moving train slows down. This is time dilation. It is not an optical illusion. It is not a mechanical flaw in clock design. Time itself flows at a slower rate for an object in motion relative to an observer at rest. The formula for time dilation, derived directly from the Pythagorean theorem applied to our light clock triangle, is given by the Lorentz factor, backslash gamma dollar backslash gamma equals backslash frac 1 backslash sqrt1 backslash frac v2c2 where v dollar is the velocity of the moving object and c dollar is the speed of light. The dilated time interval \delta t dollar experienced by the outside observer is related to the proper time interval \delta t dollar experienced by the moving observer by $delta t equals \gamma c dot \delta t dollar at everyday human speeds as such as walking down a street or flying in a commercial jet. A fraction v/c dollar is infinitesimally small, making the Lorentz factor \gamma dollar practically equal to 1. The difference in the flow of time is measured in fractions of a nanosecond, far too subtle for human perception. But as velocity v dollar approaches c dollar, v2/c2 approaches 1, the denominator approaches 0, and the factor \gamma dollar approaches infinity. If a spacecraft were to travel past Earth at 99% of the speed of light, 99 c dollar, the Lorentz factor \gamma dollar becomes roughly 7.1. For every 7 hours that pass for people on Earth, only one single hour ticks away for the astronauts aboard the spacecraft. They age 7 times slower. Their hearts beat 7 times slower. Their thoughts move 7 times slower relative to the Earth. If the spacecraft reaches 9,999 c dollar, \gamma dollar jumps to roughly 70. A journey lasting 70 years from Earth's perspective would take only one single year for those aboard the ship. And if an object could reach the exact speed of light, v equals c dollar, v2/c2 dollar would equal 1, $1 equals 0, and division by 0 yields infinity. Time for that object would freeze completely. The realization that time is flexible led Einstein to an even more unsettling insight. The concept of absolute simultaneity does not exist. In our intuitive view of the world, we assume that if two events happen at the exact same moment, everyone in the universe will agree that they happened at the same moment. Einstein proved this assumption is false through another elegant thought experiment involving a train. Imagine a long train moving smoothly along a straight railway track at high speed. A passenger, Sarah, sits precisely in the middle of a train carriage. Standing outside on the embankment is an observer, Mark. At the exact instant that the center of Sarah's train carriage passes directly in front of Mark on the embankment, 2 bolts of lightning strike the track simultaneously from Mark's perspective. A iony bolt strikes the front end of the train, point A, and 1 bolt strikes the rear end of the train, point B. Mark, standing still on the embankment, measures the distance between himself and point A to be equal to the distance between himself and point B because the light from both lightning strikes travels toward Mark at the exact same speed c dollar across equal distances. The light pulses reach Mark's eyes at the exact same instant. Mark safely concludes, the 2 lightning strikes occurred simultaneously. Now, what does Sarah, sitting inside the train, experience? Sarah is sitting in the exact middle of the carriage. When the lightning strikes occur, light beams radiate outward from point A and point B towards Sarah. However, Sarah is not standing still. She is moving forward with the train toward point A and moving away from point B because Sarah is rushing toward the incoming light beam from the front strike, point A. That light beam has a shorter distance to travel to reach her eyes. Conversely, because she is moving away from the light beam coming from the rear strike, point B, that light beam must travel across a longer distance to catch up with her. Since the speed of light is constant for Sarah inside the train, and the light from the front strike covers a shorter distance to reach her than the light from the rear strike, Sarah sees the front lightning strike happen first, and the rear lightning strike happen second to Sarah. The 2 events were not simultaneous at all. They occurred at 2 distinct moments in time. Who is correct? Was Mark right when he claimed the strikes were simultaneous, or was Sarah right when she claimed the front strike happened first? Einstein's answer was profound. Both are equally correct. There is no master observer in the universe whose perspective represents absolute truth. Simultaneous events in one frame of reference are sequential events in another frame of reference. This realization completely dissolved the notion of a universal now. The universe does not possess a cosmic ticker tape recording events in a single, global present. The sequence of events depends intimately on your state of motion through space. If time stretches when an object moves, what happens to space itself? Because speed is distance divided by time, if time dilates for a moving object, space must compensate by contracting along the direction of motion, a phenomenon known as length contraction or Lorentz contraction. Imagine an astronaut piloting a high-speed spacecraft toward a star located 10 light-years away from Earth. To observers on Earth, the distance to the star is fixed at 10 light-years. If the spacecraft travels at 99% of the speed of light, 0.99 Earth observers calculate that the journey will take approximately 10.1 years. However, consider the journey from the astronaut's perspective aboard the ship. Because of time dilation, the astronaut's personal clock ticks much slower, a factor of \gamma approx 7. $1. The astronaut measures the travel time not as 10.1 years, but as only 1.4 years. How can the astronaut cover a distance of 10 light-years in only 1.4 years without exceeding the speed of light? The answer is that from the astronaut's moving frame of reference, the universe itself has contracted. The distance between Earth and the target star is no longer 10 light-years. It has been squeezed along the line of travel by a factor of 7.1, shortening the distance to a mere 1.4 light-years. To the astronaut, the star is moving toward them at 0.99 across a distance of 1.4 light-years, taking 1.4 years to arrive. Both the Earth observer and the astronaut agree on the physics, but while the Earth observer sees time stretch, the astronaut sees space shrink. The formula for length contraction is $L equals \frac L \gamma equals L \sqrt1 \frac V2C2 where is the proper length measured by an observer at rest relative to the object, and L is the contracted length measured by a moving observer. If a sphere travels past you at 99% of the speed of light, it contracts into an flattened ellipsoid along its direction of motion. If it could reach the speed of light, its length along the line of motion would contract to absolute zero. Space itself would collapse into a two-dimensional plane. As an object approaches $, a third fundamental shift occurs: the relationship between force, mass, and energy. In classical physics, if you apply a constant force to an object, it accelerates at a constant rate F equals. If you keep pushing a spacecraft with a continuous rocket thruster, classical mechanics says its speed will increase linearly without bound. $100,000 km/s$, then $200,000 km/s$, then $300,000 km/s$, then $400,000 km/s$. But special relativity reveals that as an object's speed increases, its resistance to further acceleration, its relativistic mass or momentum, grows. The relativistic energy E$ of an object moving with velocity v$ is given by $E equals \gamma m0c2 equals \frac m0c2 sqrt1 \frac v2c2 where m0 is the object's rest mass, its mass when standing still. When the object is at rest, v equals 0. The Lorentz factor \gamma equals 1. And the equation simplifies to the most famous formula in all of science, $E m0 c2 This simple equation reveals an astonishing truth. Mass is simply concentrated, trapped energy. A small amount of mass contains a colossal amount of potential energy, scaled by the square of the speed of light c2 approx 9 times 1016 text, m2 text s2. This is the principle that powers the burning core of stars, nuclear reactors, and the deep furnace of atomic nuclei. As you pump energy into an object to accelerate it towards $, that energy adds to the total relativistic mass E$ of the system. At normal speeds, this effect is negligible. But as v$ approaches $, the energy required to achieve further speed increases dramatically. To accelerate an object with mass to 90% of c$ requires a tremendous amount of energy. To reach 99% requires far more. To reach 99.999% requires an astronomical amount of energy. To reach 100% of the speed of light, v equals c$, the denominator in the energy equation becomes zero, meaning E$ becomes infinite. To push a single pebble, a single atom, or a single electron to the exact speed of light would require more energy than exists in all the stars, galaxies, and dark matter in the entire universe combined. The speed of light c$ is not just an arbitrary wall. It is an infinite energy barrier for anything that possesses mass. In 1908, 3 years after Einstein published his special theory of relativity, a German mathematician named Hermann Minkowski, who had been one of Einstein's university professors in Zurich, realized something profound about the mathematical structure of Einstein's equations. Minkowski realized that space and time should no longer be viewed as separate entities. Instead, they were interwoven threads of a single, unified, four-dimensional continuum. Minkowski famously declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This four-dimensional framework is known today as Minkowski spacetime. In everyday life, we are accustomed to 3 dimensions of space: height, width, and depth. You can move up or down, left or right, forward or backward. To locate an event in space, you provide 3 spatial coordinates: x, y, z$. Minkowski added time as a 4th coordinate, resulting in a 4-dimensional coordinate system: x, y, z, t$. To understand how movement works in this 4-dimensional spacetime, imagine driving a car on a vast, flat, open plain. Suppose your car has a stuck cruise control set to a constant speed of 60 miles per hour. If you drive straight north, all 60 miles per hour of your speed is directed toward moving north. Your speed toward the east is 0. Now, suppose you gently turn the steering wheel slightly to the northeast. You are still moving at a total speed of 60 miles per hour, but that speed is now divided between 2 directions. You are moving north at, say, 50 miles per hour and east at roughly 33 miles per hour. Because you reallocated some of your speed toward the east, your speed toward the north slowed down. If you turn the wheel completely to the east, your speed toward the east becomes 60 miles per hour, and your speed toward the north drops to absolute zero. Minkowski showed that every object in the universe is doing something remarkably similar, but inside 4-dimensional spacetime. In Minkowski spacetime, every object is always moving at one single, unchangeable absolute speed through spacetime. The speed of light, c$. Think about what this means for you right now, sitting or lying in a quiet room, feeling completely motionless. Because you are stationary relative to your room, your speed through the 3 dimensions of space, x, y, z$, is 0. Therefore, 100% of your motion through spacetime is directed into the 4th dimension. Time. You are traveling through time at the maximum possible rate. Your clock is ticking at its maximum speed. However, if you get up and begin moving through space, you are turning your steering wheel in spacetime. Some of your fixed motion through spacetime is diverted away from the dimension of time and reallocated into the dimensions of space. Because you are now using a portion of your fixed spacetime speed to move through space, your speed through time must slow down. The faster you move through space, the less speed you have left over to move through time. This is the ultimate, intuitive explanation of time dilation. Time slows down when you move through space because you have reallocated your motion through the 4-dimensional geometry of spacetime. If an object accelerates through space until it travels at the speed of light c$ through space, 100% of its spacetime velocity is consumed by spatial motion. It has 0 motion left over for time. Motion through time drops to absolute 0. Time stands frozen. This is why a photon, traveling through space at c$, experiences no time. It moves purely through space, spending none of its velocity budget on the temporal dimension. The mathematical distance between 2 points in three-dimensional space is given by the classic Euclidean distance formula based on the Pythagorean theorem, $d2 backslash delta x2 plus backslash delta y2 plus backslash delta z2 $. This spatial distance d$ is different for observers moving relative to one another due to length contraction. However, Minkowski discovered a new, invariant quantity in four-dimensional spacetime that remains identical for all observers, no matter how fast they are moving. This is called the spacetime interval, backslash delta S2 $, backslash delta S2 equals C2 backslash delta T2 plus backslash delta X2 plus backslash delta Y2 plus backslash delta Z2 $. Notice the minus sign before the time component, C2 backslash delta T2. This negative sign is the fundamental geometric signature that separates the temporal dimension from spatial dimensions. It is the reason space and time are not identical, yet remain intimately tied together. While two observers in relative motion will measure different values for spatial distance, backslash delta x$, and different values for time elapsed, backslash delta t$, when they combine those values into the spacetime interval formula, they will calculate the exact same value for backslash delta S2 $. The spacetime interval is an invariant truth an objective reality anchored in the geometry of the universe, independent of who is observing it. From this four-dimensional geometry emerges one of the most elegant concepts in modern physics, the light cone. Imagine standing at a single point in spacetime, here and now. This point is called the event. If you emit a sudden pulse of light from your position, that light spreads outward in all directions through space like an expanding spherical bubble. If we represent three-dimensional space as a flat two-dimensional plane, horizontal axis, and time as a vertical axis pointing upward into the future, that expanding sphere of light traces out a smooth, three-dimensional cone opening upward. The future light cone. Everything inside your future light cone represents regions of spacetime that you can potentially reach, influence, or communicate with in the future, traveling at or below the speed of light. The outer surface of the cone itself is formed by light rays traveling at speed c$. Now, look downward into the past. There exists a second cone opening downward, its tip meeting your present moment at here and now. This is the past light cone. It consists of all light rays and signals from across the universe that had enough time to travel to your current position. Everything inside your past light cone represents every cause, every star, every photon, and every event that could possibly have influenced your present moment. What lies outside these two light cones, the region outside the future, and past light cones is called elsewhere. Elsewhere consists of events in spacetime that are separated from your current moment by a spatial distance so vast that even a signal traveling at the speed of light could not link them. For example, if a star in the Andromeda galaxy explodes right now in galactic time, that event sits in your elsewhere. Because Andromeda is 2.5 million light-years away, the light from that explosion will take 2.5 million years to reach Earth. For the next 2.5 million years, that explosion remains strictly outside your light cone. Because no signal or influence can travel faster than c$, events in your elsewhere can have no causal connection to your present moment. They cannot affect you, and you cannot affect them. They exist in a domain of physical independence, separated by the cosmic buffer of spacetime geometry. The boundary of the light cone is the absolute divide between cause and effect. It organizes the universe into a strict, logical hierarchy. It ensures that no event can influence its own past, and no cause can be outrun by its effect. As we sink deeper into the quiet reality of Minkowski spacetime, a profound philosophical truth begins to take shape, an irony that challenges how we experience life itself. In our everyday conscious experience, time feels like a moving river. We feel as though the past is gone forever, burned away like smoke. The future is unwritten and non-existent, and we are continually riding a razor-thin edge of the present sliding forward through time. This philosophical view is known as presentism. However, the geometry of special relativity demands a radically different view of reality, the block universe hypothesis, or eternalism. Because special relativity proves that simultaneity is relative, two observers in relative motion do not agree on which events are happening now. Imagine an observer sitting still on Earth, and an alien in a distant galaxy billions of light years away riding a bicycle slowly away from Earth. Because of the vast distance and the alien's slight motion, the alien's plane of simultaneity their slice of now cuts through Earth's time stream at a different angle than ours. For the alien moving away from Earth, their now might align with events on Earth that happened hundreds of years in the past, such as the construction of ancient cities or early astronomical discoveries. If the alien turns around and rides their bicycle toward Earth, their plane of simultaneity tilts forward into our future, aligning with events on Earth that will not happen for hundreds of years to come. If both the past and the future are included in the now of different valid observers moving through the cosmos, then the past, present, and future must all exist simultaneously in the four-dimensional structure of spacetime. In the block universe model, spacetime is a massive, static, four-dimensional block containing all of space and all of time. The Big Bang, the formation of the Earth, your birth, the moment you are listening to these words right now, and the distant end of the universe are all permanently etched into the geometry of spacetime. Every moment that has ever occurred, or will ever occur, is eternally present in the four-dimensional tapestry. When Albert Einstein lost his lifelong friend, the physicist Michel Besso, in March 1955, just a few weeks before Einstein's own death, Einstein wrote a comforting letter to Besso's family. In it, he offered a quiet, profound reflection born directly from his physics. Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. From the objective perspective of four-dimensional spacetime, time does not flow. Events do not vanish when they pass into the past, nor are future events waiting to be created out of nothingness. Your life is not a fleeting spark that vanishes down a moving river. Your life is an enduring, four-dimensional line, a world line, woven permanently into the fabric of the universe. Every smile, every quiet night, every deep breath, and every thought you have ever held is an indelible, unchangeable thread in spacetime, shining permanently in the cosmic fabric. Allow your mind to relax into this vast, serene vision of existence. We began our journey with a single paradox: why light moves at an unchanging speed regardless of motion. To solve that puzzle, we stepped through the looking glass of special relativity. We saw space shrink, time stretch, and the rigid walls of Newtonian reality dissolve away. We saw that space and time are not cold, isolated voids, but threads woven into a single, breathtaking tapestry, a Minkowski spacetime. We learned that speed is a reallocation of motion through four dimensions, and that the ultimate speed limit, c, is the invariant geometry protecting cause and effect across the vastness of space. In the quiet of this night, as you lie completely still, remember that you are traveling through time at its maximum possible speed. You are riding your world line smoothly through four-dimensional spacetime. Every atom in your body is moving through the temporal dimension with absolute, unbroken harmony. The universe around you is structured, stable, and deeply quiet. The cosmic speed limit holds firm, safeguarding the sequence of reality, preserving the past, and holding the future in peaceful balance. In our next chapter, we will leave behind the smooth, continuous geometry of special relativity to venture down into an entirely different world, microscopic, chaotic, and mysterious realm of the subatomic. There, we will discover that while special relativity keeps macro-scale reality ordered and predictable, the quantum world harbors secret, instant connections that would baffle even Einstein himself. But for now, there is nothing you need to compute, nothing you need to measure, and nowhere you need to travel. Allow the quiet geometry of spacetime to wrap around you like a soft, weightless blanket. Let your thoughts settle, let your body rest, and drift peacefully into the deep, timeless dark of the universe. As your mind settles into the quiet, four-dimensional geometry of spacetime, we prepare to leave behind the smooth, deterministic world of macrophysics. In our previous exploration, we marveled at the elegant, continuous fabric woven by Einstein's special relativity universe where space contracts, time dilates, and every event is etched into an unbroken, four-dimensional block. That macrocosmos is orderly, predictable, and governed by flawless geometric laws. Yet if you zoom in past the stars, past the planets, past microscopic dust and individual cells, down into the hidden subatomic realm, that smooth geometric curtain collapses completely. Below the threshold of the atom, nature drops its deterministic mask and reveals a world so strange, so counterintuitive, and so deeply probabilistic that it shattered the foundational beliefs of physics itself. Welcome to the subatomic world, the domain of quantum mechanics. To understand why the subatomic world sparked a revolution, we must look at the landscape of science at the close of the 19th century. Physicists believed they were approaching the final completion of their field. Isaac Newton's laws of motion explained the mechanical orbits of planets and the fall of apples with equal precision. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single electromagnetic wave theory. Thermodynamics explained heat and energy transfer. The cosmos was viewed as a massive, clockwork machine. If you knew the exact position and momentum of every particle in the universe at one moment, classical physics asserted that you could use the laws of nature to calculate the entire past and future with absolute certainty. However, a subtle, persistent crisis was lurking at the margins of physical experiments, a paradox, known as the ultraviolet catastrophe. When physicists tried to calculate the radiation emitted by an idealized hot object, a blackbody, using classical wave theory, the mathematics broke down catastrophically. Classical physics predicted that a hot object should emit an infinite amount of short wavelength energy, such as ultraviolet light, X-rays, and gamma rays. According to classical equations, every time you turned on an oven or lit a candle, it should blast the room with an infinite torrent of lethal ultraviolet radiation. In reality, an oven simply glows with a warm, comforting red heat. Classical mechanics was predicting a mathematical infinity where nature produced a soft, finite glow. The man who resolved this paradox was a quiet, meticulous German physicist named Max Planck. In December 1900, Planck presented a radical theoretical fix. To prevent the calculations from blowing up to infinity, Planck proposed an assumption that he initially considered a mere mathematical trick. What if energy is not a continuous, smooth fluid? For centuries, physics assumed that energy could be absorbed or emitted in any arbitrary amount, like water flowing continuously from a faucet. Planck suggested instead that energy is exchangeable only in tiny, indivisible, discrete packets or bundles. He called these packets quanta. Planck introduced a fundamental equation relating the energy E of a quantum to the frequency omega of its wave. E equals h omega, where h is a brand new fundamental constant of nature, now known as Planck's constant, h as 626 square root o acute 10. A 34. Not j a tilde o umlauts. Because h is an extraordinarily minuscule number, energy quanta are so tiny that in our macroscopic lives, energy appears smooth and continuous, just as a sandy beach looks like a smooth sheet of gold from an airplane high above. But zoom in close enough, and the continuous sheet dissolves into individual, countable grains. Higher frequency light, such as ultraviolet light, requires a larger quantum of energy E equals h omega to be emitted, because a hot oven does not possess enough thermal energy to produce these large, indivisible packets of ultraviolet quanta. The emission drops off safely to zero. The ultraviolet catastrophe was solved, and the quantum age was born. At first, Planck believed his quanta were simply a property of how atoms absorbed and emitted radiation, not a fundamental property of light itself. But in 1905, Albert Einstein took Planck's idea a monumental step further. Einstein was investigating the photoelectric effect ith phenomenon, where shining light on a metal plate causes electrons to be knocked loose, generating an electric current. Classical wave theory predicted that if you used dim light, you could simply wait for energy to build up continuously on the metal's surface until an electron gained enough energy to break free. Furthermore, classical theory suggested that making the light brighter, increasing its wave amplitude, would knock electrons out with higher energy. Experiments showed the exact opposite. Dim blue light knocked electrons out instantly with high kinetic energy, while extremely bright, blinding red light could shine on the metal for 1,000 years without releasing a single electron. Einstein realized that light itself is quantized. A beam of light is not a continuous wave, but a stream of localized packets of energy A particles of light that we now call photons. A photon of red light carries a low frequency omega, meaning its energy E equals h omega is small a too small to break the chemical bond holding an electron to the metal, no matter how many red photons you hurl at it. But a single photon of high-frequency blue light carries a large bundle of energy, striking an electron like a localized billiard ball and knocking it free in a single, instantaneous collision. Einstein won his only Nobel Prize in physics not for his theories of relativity, but for explaining the photoelectric effect through the light quantum hypothesis. Light, long believed to be purely a wave, was behaving like a stream of localized particles. This birthed the central mystery of quantum physics, wave-particle duality. If light A traditionally understood as a wave A could behave like a particle, could entities traditionally understood as solid particles as such as electrons I behave like waves? In 1924, a French nobleman and physicist named Louis de Broglie made a breathtaking proposal in his doctoral thesis. De Broglie suggested that nature possesses a deep, underlying symmetry. If light waves have particle properties, then material particles with mass must also possess wave properties. De Broglie derived an equation for the wavelength OEA of any moving object with momentum p. OEA equals P H L, where h is Planck's constant and p equals mv is the momentum of the object. For a macroscopic object like a thrown baseball or a moving vehicle, the mass m is so large that the de Broglie wavelength OEA is unimaginably tiny trillions of times smaller than an atomic nucleus A, making its wave-like nature completely undetectable. But for an electron, whose mass is microscopic m, E, L, and 9, 11 square root O cute 10, A 31, not kg, the de Broglie wavelength is roughly the size of an atom itself. An electron does not orbit an atomic nucleus like a tiny marble. It wraps around the nucleus as a three-dimensional standing wave. To witness wave-particle duality in its most mesmerizing form, we must examine the famous double-slit experiment. Imagine a barrier with two thin, parallel vertical slits cut into it. Behind the barrier stands a detector screen. If you shoot macroscopic objects A like small paint droplets A at the two slits, some droplets hit the barrier and bounce back, while others pass through the slits and strike the detector screen behind. On the screen, you observe two distinct, solid vertical bands of paint corresponding directly to the shapes of the two slits. This is classic particle behavior. Now imagine sending a wave A such as a water wave A toward the two slits. As the wave hits the barrier, two new circular wave fronts ripple outward from the two slits. As these two sets of waves overlap, their crests and troughs interact. Where crest meets crest, they reinforce each other, constructive interference. Where crest meets trough, they cancel each other out, destructive interference. When the wave energy hits the back screen, it leaves a complex pattern of multiple alternating bright and dark vertical bands, an interference pattern. This is classic wave behavior. Now, what happens if we fire subatomic objects A such as electrons A at the double slits? If electrons are solid particles, they should produce two distinct vertical bands on the detector screen. But when physicists perform the experiment, each electron strikes the detector screen as a single, localized dot, like a tiny particle. However, as thousands of electrons are fired through the slits one after another, an extraordinary pattern gradually emerges on the screen dot by dot. The individual particle strikes do not form two simple lines. They assemble into an interference pattern, a series of alternating bright and dark bands. Each electron seems to travel through the slits as a wave of probability, interfering with itself, and then collapses into a single localized particle the moment it strikes the detector screen. Physicists were baffled. To test how this could happen, they sent the electrons through the apparatus one at a time, waiting minutes between each firing so that no two electrons were in the device simultaneously. There was no other electron to collide or interfere with. Yet, even when fired one by one, the individual electrons still built up an interference pattern over time on the detector screen. A single electron was somehow passing through both slits at the exact same time, interfering with its own wave-like trajectory, and deciding where to land based on the mathematics of wave interference. Perplexed, physicists decided to place a microscopic detector at the slits to observe which slit the electron actually passed through. The moment they turned on the detector to watch the electron, nature changed its behavior. As soon as a measurement was made to determine the electron's path, the wave-like interference pattern on the back screen vanished instantly. The electrons stopped passing through both slits as waves and began behaving like solid classical marbles, passing through either the left slit or the right slit, producing two simple vertical bands. The mere act of observation destroyed the wave interference. Measurement forced the quantum system to choose a single, classical reality. To describe this strange wave-like behavior mathematically, the Austrian physicist Erwin Schur-Dinger formulated the fundamental equation of non-relativistic quantum mechanics in 1925, the Schur-Dinger equation. I ni accessibility accessibility o registered xt equals age o registered xt, where O registered, xt is the wave function of the quantum system, I is the imaginary unit, ni equals h/2 a umlaut is the reduced Planck constant, and age is the Hamiltonian operator representing total energy. The wave function O registered psi is the central object in quantum theory. But what does the wave function actually represent? Is it a physical wave of matter, like a ripple in water? The answer came from the German physicist Max Born, who introduced the Born rule. Born proposed that the wave function O registered itself is not a physical substance. Rather, its absolute square, a pound O registered, xt a pound, 2, represents a probability density. The wave function is a wave of pure probability. Before you make a measurement, an electron does not exist at a single, precise location in space. Instead, Its wave function spreads out through space, evolving smoothly and deterministically according to the Schrödinger-Delta-Dinger equation. The wave function describes all the places the electron could be, along with the varying probabilities of finding it there. Where the wave function's amplitude is large, there is a high probability of finding the electron upon measurement. Where the amplitude is zero, there is zero probability of finding it. Before measurement, the electron exists in a state of superposition, a simultaneous blend of all possible outcomes. It is not here or there. It is distributed across a cloud of potential realities. The moment an observation or measurement is made, the wave function undergoes what physicists call the collapse of the wave function. The vast cloud of possibilities collapses instantly down to a single point, and a single, definite reality materializes. This transition from probability to certainty introduced a fundamental limits to human knowledge, formalized in 1927 by the German physicist Werner Heisenberg. The Heisenberg uncertainty principle. Heisenberg proved that in the quantum world, there are pairs of physical properties, A known as complementary variables, A that cannot both be known with absolute precision at the same time. The most famous pair is position x and momentum p. Heisenberg derived the famous inequality OX OIP a circumflex 2 ni a, where OX is the uncertainty in position and OIP is the uncertainty in momentum. This principle is not a limitation of our measuring instruments. It is an inherent property of the fabric of quantum reality. If you attempt to measure the precise position of an electron, OX UI0, by bouncing a photon off it, that photon imparts an unpredictable kick to the electron, throwing its momentum into chaos OIP UI. Conversely, if you measure its exact momentum, its wave function spreads out across space, leaving its position completely unknown. You can know where a subatomic particle is, or you can know how fast it is moving, but nature forbids you from knowing both with absolute certainty at the exact same moment. A similar uncertainty relation exists between energy E and time t. OEO at a circumflex 2 ni a. This energy-time uncertainty relation reveals something astonishing about the empty vacuum of space. For an extremely brief duration of time OIT, a quantum system can borrow a large amount of energy OE directly out of nothingness, provided that energy is paid back before the uncertainty window closes. Because of this, the empty vacuum of space is not a dead, quiet void. At the subatomic scale, the vacuum is a boiling, churning sea of quantum fluctuations, where virtual particles and antiparticles constantly pop into existence out of nothing, exist for a fleeting fraction of a femtosecond, and annihilate back into the dark. The universe at its smallest scales is perpetually trembling with microscopic activity. This wave-like, probabilistic nature of subatomic reality leads to a phenomenon that powers the stars themselves: quantum tunneling. In classical physics, if a ball does not possess enough kinetic energy to roll over a hill, it will hit the side of the hill and roll back down every single time. The hill acts as an impenetrable energy barrier. In quantum mechanics, however, an electron or proton approaching an energy barrier is described by a wave function O registered. As the wave function encounters the barrier, the wave does not stop abruptly at the boundary. Instead, the wave function decays exponentially inside the barrier wall. If the energy barrier is thin enough, the wave function does not drop completely to zero before reaching the other side. A small fraction of the wave function leaks through, emerging on the far side of the wall. Because a pound O registered a pound 2 on the far side of the wall is greater than zero, there exists a finite probability that the particle will simply vanish from one side of an impenetrable barrier and materialize on the other side, without ever climbing over it. The particle has tunneled directly through solid energy space. Quantum tunneling is not a theoretical fantasy. It is a vital mechanism of our physical existence. Inside the core of our sun, temperatures reach 15 million degrees, and pressures are immense. Yet, classical physics shows that the electrostatic repulsion between two positively charged hydrogen protons is too strong for them to get close enough to fuse together. If classical physics were the whole story, the sun could not ignite, fusion would fail, and the Earth would be a frozen, lifeless rock. Because of quantum tunneling, a tiny fraction of the protons in the sun's core tunnel through the electrostatic barrier holding them apart. Even though the probability of a single proton tunneling is infinitesimally small, the colossal number of collisions occurring every second in the solar core guarantees a steady, continuous rate of nuclear fusion. The sun shines, emitting the gentle, golden warmth that cradles life on Earth, precisely because subatomic particles are continually tunneling through impossible walls in the quiet dark. Despite its staggering experimental successes, the probabilistic nature of quantum mechanics created a deep, bitter ideological divide among the world's greatest physicists. At the center of this debate stood Albert Einstein. Einstein had ignited the quantum revolution with his explanation of the photoelectric effect, but he grew deeply unsettled by the direction the theory was taking under the leadership of Niels Bohr and the Copenhagen interpretation. The Copenhagen interpretation asserted that physical reality does not exist in a definite state prior to measurement. Nature, at its core, was fundamentally governed by intrinsic chance, uncertainty, and probability. Einstein vehemently rejected this view. He believed that the wave function was simply an incomplete description of reality, that there must exist hidden, deeper variables that physics had not yet discovered. Einstein insisted that the universe was deterministic, objective, and independent of conscious observers. In a famous series of letters and debates with Niels Bohr, Einstein expressed his deep philosophical objection in a phrase that resonated through the history of science. Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not play dice. Niels Bohr famously replied, "Einstein, stop telling God what to do." This clash between Einstein's deterministic worldview where space is smooth, causality is strict, and objects exist with definite properties and Bohr's quantum worldview where reality is grainy, probabilistic, and forged by observation became the greatest debate in the history of science. Einstein spent the rest of his life searching for a unified field theory that could smooth away quantum probability and unite gravity with electromagnetism into a single, deterministic continuum. He refused to accept that the universe at its most fundamental level was a casino governed by rolling dice. Yet experiment after experiment over the past century has confirmed the predictions of quantum mechanics with staggering mathematical precision. Today, quantum mechanics is the most thoroughly tested and commercially applied theory in human history. The silicon microprocessors powering our computers, the fiber optic lasers carrying our communications, the magnetic resonance imaging, MRI, machines scanning our bodies, and the atomic clocks tracking our time all function strictly because of the laws of quantum physics. Allow your mind to take a slow, deep breath and absorb the breathtaking contrast of the cosmos we inhabit. On the grandest scales of space and time, relativity paints a picture of majestic, unbroken harmony. Galaxies spin in structured cosmic webs, light curves smoothly around massive suns, and the four-dimensional tapestry of spacetime holds the past, present, and future in peaceful balance. Yet down at the subatomic foundation of that very same universe, reality breathes with quantum potential. Particles exist as clouds of possibilities, energy flows in indivisible quanta, waves tunnel through impossible barriers, and the vacuum itself trembles with zero-point energy. The cosmos is both a flawless geometric stage and a vibrant quantum ocean. As you lie here in the quiet sanctuary of the night, realize that every atom in your body is a masterpiece of this dual architecture. The electrons surrounding your cells wrap themselves in stable quantum standing waves, holding your physical structure together. The light from distant stars traveling across the light years reaches your eyes as localized quantum photons, carrying ancient messages from the deep past. There is nothing you need to resolve, nothing you need to measure, and no probabilities you need to calculate. The quantum fields are holding their potentials in perfect, silent balance. The subatomic world is maintaining its quiet, foundational dance. Allow your thoughts to settle into the deep, peaceful stillness beneath the noise of daily life. Let your body rest, let your awareness soften, and drift smoothly into the vast, calm ocean of the sleeping universe. Allow your body to sink even deeper into the stillness of the dark. Let your breathing remain slow, rhythmic, and natural, like the steady, gentle rise and fall of ocean tides. In our previous chapters, we traveled across two radically different visions of physical reality: the smooth, four-dimensional geometry of Einstein's special relativity, and the flickering, probabilistic realm of the quantum subatomic world. These two pillars of modern science were born at the dawn of the 20th century, yet they seem to describe two completely incompatible universes. On one side stood a macrocosmos of deterministic certainty, where space contracts, time dilates, and cause leads flawlessly to effect. On the other side stood a microcosmos of inherent chance, where particles exist as clouds of probability, wave functions collapse upon observation, and uncertainty is built into the foundational source code of nature. Naturally, these two visions could not coexist without a monumental clash. What followed was the intellectual battle of the century, a profound, legendary debate between the two towering titans of modern physics, Albert Einstein and Niels Bohr. This was not merely a disagreement over mathematical equations or laboratory measurements. It was a battle for the soul of physics itself. It was a philosophical and physical war over the fundamental nature of reality. Is the universe objective, deterministic, and independent of our observation? Or is reality created, defined, and brought into existence by the very act of measurement? To witness this clash unfold, we must travel back in time to October 1927, to the quiet, rain-swept streets of Brussels, Belgium. There, at the Hotel Metropole, 29 of the world's greatest scientists gathered for the 5th Solvay International Conference. 17 of those 29 attendees had won or would go on to win the Nobel Prize. Among them were Marie Curie, Max Planck, Erwin Delta-Dinger, Werner Heisenberg, Louis de Broglie, Paul Dirac, and standing at the opposing poles of the great debate, Albert Einstein and Niels Bohr. The theme of the 1927 conference was electrons and photons. The newly formulated Copenhagen interpretation of quantum mechanics, crafted primarily by Niels Bohr and Werner Heisenberg, was being presented to the world as a complete, definitive framework. Bohr argued that physics was no longer about discovering what nature is. Physics was about what we can say about nature. In Bohr's view, it was meaningless to ask what an electron is doing when no one is looking at it. Prior to measurement, a quantum particle possesses no definite position, no definite momentum, and no definite reality. It exists only as a mathematical wave function, a cloud of pure possibilities described by the Delta-Dinger equation. Only when a macroscopic detector interacts with the quantum system does the wave function collapse, forcing nature to pick a single, random outcome. Einstein listened to these assertions with growing unease and profound skepticism. To Einstein, the Copenhagen interpretation was a surrender of the ultimate goal of science. Since his early youth, Einstein had believed in a universe that was objective, rational, and completely independent of human observers. He believed that the moon continues to exist in a definite place in space, whether a mouse looks at it or not. To suggest that a subatomic particle has no definite position until a conscious observer or detector looks at it felt to Einstein like physics slipping into mysticism. And so, the 1927 Solvay Conference transformed into an intellectual arena. Every morning at breakfast in the dining room of the Hotel Metropole, Einstein would arrive with a brilliant, newly devised thought experiment, Jettington experiment, signed to expose a logical flaw or contradiction in the Copenhagen interpretation and break Heisenberg's uncertainty principle. Einstein's strategy was elegant. He sought to construct a hypothetical experiment that could measure both the position and momentum of a subatomic particle simultaneously, with absolute precision. If he could prove that both properties existed with certainty at the same time, he would prove that quantum mechanics was incomplete, that hidden variables must exist beneath the probabilistic surface. Throughout the morning, Einstein would lay out his thought experiment over coffee and rolls. He would present a scenario so clever, so meticulously constructed, that it seemed to trap the quantum theorists in an inescapable paradox. Bohr would sit quietly, listening intently, his mind churning over the puzzle. Joining Bohr was his brilliant young colleague, Werner Heisenberg. The quantum theorists would leave the breakfast table in a state of distress, spending the rest of the day packing the streets of Brussels, analyzing every detail of Einstein's challenge. One of Einstein's most famous attacks during the 1927 conference involved a variation of the classic double-slit experiment. Einstein invited Bohr to imagine a barrier containing a single slit, placed in front of a second barrier containing two slits. A beam of particles such as photons or electrons fired toward the first single slit. As a single photon passes through the first slit, it experiences a slight deflection, scattering toward one of the two slits in the second barrier. Einstein argued that because the photon possesses momentum, passing through the first slit must impart a tiny physical recoil to the first screen itself. Einstein proposed mounting the first screen on delicate springs or sensitive detectors capable of measuring this microscopic recoil. By measuring the direction of the recoil of the first screen, an experimenter could determine precisely which of the two slits the photon was heading toward, without disturbing the photon's path. Then, when the photon passed through the second barrier and struck the back screen, it would produce an interference pattern. Einstein believed he had found the ultimate trap. He had devised a scheme to know which path the particle took by measuring the recoil of the first screen, while simultaneously preserving its wave-like interference pattern on the back screen. This would directly violate Heisenberg's uncertainty principle, which stated that you cannot observe the particle's path without destroying the wave interference. Bohr spent an agonizing afternoon analyzing Einstein's proposed apparatus. By evening, as the scientists gathered in the hotel lounge after dinner, Bohr delivered his counterproof. Bohr pointed out a fatal flaw in Einstein's reasoning. Einstein had treated the particle as a quantum object, but he had treated the first screen and its measuring apparatus as a rigid, classical object. Bohr demonstrated that if the first screen is sensitive enough to measure the tiny recoil imparted by a single photon, the screen itself must be treated as a quantum object. Because the screen is a quantum object, its own position and momentum are bound by Heisenberg's uncertainty principle. Oix, screen, a tilde umlaut oip, screen, a circumflex, 2, ni, a. To measure the recoil momentum of the screen with enough precision to determine which slit the photon entered, the uncertainty in the screen's momentum, OIP, screen, A, must be extremely small, but if OIP Screen A is extremely small. The uncertainty in the screen's physical position OX. Screen A becomes unavoidable and large. Because the screen's position is uncertain, the exact location of the first slit wobbles. This microscopic spatial wobble introduces an unpredictable phase shift into the photon L's wave function as it passes through. When you calculate the mathematics, this phase shift completely washes out and destroys the interference pattern on the back screen. Bohr had turned Einstein L's own logic against him. If you measure the recoil of the screen to know the path, the uncertainty in the screen's position destroys the wave interference. If you keep the screen rigidly fixed so its position is known and interference is preserved, you lose the ability to measure the recoil momentum. The uncertainty principle remained unbroken. Day after day, the ritual repeated. Einstein would present a new, brilliant thought experiment at breakfast. Bohr and Heisenberg would analyze it through the long afternoon, and by dinner, Bohr would deliver a flawless defense of the quantum realm. It was during these heated, late-night discussions in the lounge of the Hotel Metropole that Einstein, frustrated by Bohr's insistence on intrinsic randomness, uttered his immortal line, "God does not play dice with the universe," to which Bohr famously responded with quiet, unyielding authority. Einstein stopped telling God what to do. When the 1927 Solvay conference concluded, the scientific community widely considered Bohr the victor. The Copenhagen interpretation stood firm, yet Einstein remained entirely unconvinced. He conceded that quantum mechanics was mathematically consistent and experimentally accurate, but he refused to accept that it was the final, complete description of reality. To Einstein, quantum mechanics was a brilliant statistical tool, an intermediate stepping stone toward a deeper, deterministic truth. 3 years passed. In October 1930, the Sixth Solvay Conference convened in Brussels. Einstein arrived with his ultimate weapon, a thought experiment so devastatingly clever that he believed it would permanently dismantle the Copenhagen interpretation. This masterpiece of theoretical physics became known as Einstein-L's light box, or Einstein-L's photon box. Einstein targeted the energy-time uncertainty principle, which states that the uncertainty in a system's energy, OEE, and the uncertainty in the time interval over which that energy is measured, OIT, are bound by the relation OEE tilde ohm not OIT a circumflex. 2. Ni. Einstein designed a thought experiment intended to measure both the energy of a photon and the exact time it was emitted with absolute, arbitrary precision, making OEE a tilde O umlaut OIT equal to 0. Imagine a box filled with electromagnetic radiation, a box of light. Inside the box is a clock connected to a mechanical shutter that covers a small hole in the side of the box. The mechanism is set up so that the clock opens the shutter for a brief, precise fraction of a second, allowing a single, solitary photon to escape from the box, and then immediately closes the shutter. Because the clock controls the shutter, the exact time t, at which the photon left the box is known with absolute precision. The time uncertainty OIT can be made as small as humanly possible. Now, how do we measure the exact energy, E, of that escaped photon? Einstein recalled his own famous equation from special relativity. E equals mc. 2. Energy and mass are equivalent. Einstein proposed weighing the entire box on a precision scale before the photon is released. The box has a certain mass m. 1. Then the shutter opens and closes, releasing the single photon. As the photon escapes, it carries away a tiny amount of energy E. Because the box has lost energy E, it has also lost a corresponding amount of mass. OM equals C 2 E L. After the photon has departed, we weigh the box a second time on the precision scale, obtaining a lighter mass m. 2. The difference in mass OM equals m. 1. M. 2. Allows us to calculate the exact energy of the escaped photon E equals OM A tilde erg. 2. With infinite precision. Einstein stood back. The time of emission was measured by the clock. The energy of the photon was measured by the scale. Both quantities were measured independently and with absolute precision. The product OE A tilde O umlaut OIT could be brought arbitrarily close to zero, violating the Heisenberg uncertainty principle. When Einstein presented the light box experiment at the conference, the quantum theorists were stunned. Leon Rosenfeld, a Belgian physicist who attended the conference, recorded the reaction of the scientists that evening. It was a real shock for Bauer. He did not see the solution at once. During the whole evening he was extremely unhappy, walking from one person to another and trying to persuade them that it couldn't be true, that if Einstein was right it would mean the end of physics, but he could find no refutation. I shall never forget the vision of the two antagonists leaving the club. Einstein, a tall, majestic figure, walking quietly, with a somewhat ironical smile, and Bauer trotting by his side, full of excitement. Bauer spent a sleepless night packing his hotel room. He examined every single component of Einstein's light box, the radiation, the shutter, the clock, the spring scale, and the gravitational field of the Earth holding the scale. As dawn broke over Brussels, Bauer realized something extraordinary. Einstein had made a profound oversight in his own thought experiment, and the key to dismantling Einstein's trap lay in Einstein's own greatest masterpiece, the theory of general relativity. When the conference reconvened the following morning, Bauer stepped up to the blackboard to deliver his response. Bauer drew a detailed diagram of Einstein's light box, mounted on a spring scale. Bauer pointed out that to weigh the box before and after the photon is released, the box must be suspended by a spring in a gravitational field. When the single photon escapes, the box loses mass OM and becomes lighter. Because the box is now lighter, the spring pulls the box slightly upward in the gravitational field. Now, Bauer invoked Einstein's theory of general relativity. Under general relativity, gravity warps spacetime, causing time to dilate. A clock placed deeper in a gravitational field, closer to the Earth, ticks slower than a clock placed higher up in a gravitational field. This phenomenon is known as gravitational time dilation. Because the loss of the photon caused the box to move upward in Earth's gravitational field, the clock inside the box moved to a position of slightly weaker gravity. As a result, the rate at which the clock ticked changed. Bauer walked the audience through the rigorous mathematical derivation. The uncertainty in measuring the weight of the box, delta, leads to an uncertainty in the vertical position of the box on the spring scale, deltax. Through Heisenberg's uncertainty principle applied to the spring's momentum and position, this spatial uncertainty introduces an inescapable uncertainty in the clock's vertical position in the gravitational field. When Bauer calculated the exact gravitational time dilation caused by this vertical displacement over the time interval of the measurement, he arrived at a breathtaking mathematical result. Delta, gravitational, approximately 2 delta, letter 210f, which rearranges directly into delta delta greater or equal to 2, letter 210f. The uncertainty principle was saved, and it was saved by using Einstein's own theory of general relativity against his own thought experiment. Einstein had forgotten to account for the gravitational time dilation of his own clock when it moved upward on his own scale. When Bauer finished his demonstration, the room fell silent. Einstein looked at the blackboard, recognized the mathematical perfection of Bohr's argument, and quietly smiled. He accepted the defeat of the light box thought experiment. He conceded that the Copenhagen interpretation was logically airtight and mathematically self-consistent. Yet despite this second defeat, Einstein's fundamental objection never wavered. Einstein was not a stubborn man clinging to outdated ideas. He was a visionary guided by a profound philosophical conviction. He accepted that quantum mechanics worked flawlessly as a practical tool, but he refused to accept that reality itself was inherently fragmented, incomplete, and observer-dependent. Einstein shifted his strategy. He stopped trying to prove that quantum mechanics was wrong or self-contradictory. Instead, he set out to prove that quantum mechanics was incomplete, that there existed a deeper, objective reality beneath the quantum wave function, waiting to be discovered. This philosophical divide between Einstein and Bohr highlights two fundamentally different ways of viewing our place in the cosmos. Einstein championed local realism. Realism asserts that physical objects possess definite, objective properties, like position, velocity, and mass, whether they are being observed or not. The world exists independently of consciousness or measurement. Locality asserts that physical objects are influenced only by their immediate surroundings. An event happening at one point in space cannot instantaneously influence an event at another distant point without a physical signal traveling between them at or below the speed of light. C. Bohr, on the other hand, championed complementarity and anti-realism. Bohr argued that the classical concepts of position, momentum, particle, and wave are simply complementary lenses through which human beings attempt to interpret a quantum reality that lies beyond human language. In Bohr's view, a physical property does not belong to the particle alone. It belongs to the entire experimental arrangement, including the observer and the detector. You cannot separate the phenomenon from the instrument measuring it. When asked whether he believed the quantum world truly existed in the absence of observation, Bohr replied that there is no quantum world. There is only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns only what we can say about nature. This debate between Einstein and Bohr was not resolved during their lifetimes. When Einstein passed away in Princeton in April 1955, a draft of his latest paper on unified field theory sat on his nightstand, unfinished. He was still searching for the deterministic foundation of reality until his final breath. When Niels Bohr passed away in Copenhagen 7 years later, in November 1962, a drawing remained on the blackboard in his study. It was a drawing of Einstein's light box. Even in his final days, Bohr was still thinking about his great friend, his greatest challenger, and the debate that defined their lives. Their intellectual battle was conducted with deep mutual respect, warmth, and admiration. Einstein once wrote of Bohr, "He is one of the greatest scientific minds of our time, an extraordinarily sensitive and noble soul." And Bohr wrote of Einstein, "The discussions with Einstein were among the most inspiring experiences of my life. His penetrating mind and unwavering devotion to truth forced us to deepen our understanding of reality at every turn." As you lie here in the quiet dark, listening to the gentle rhythm of your breath, allow the depth of this historical clash to wash over your awareness. Think of those two magnificent minds walking together through the quiet streets of Brussels, arguing passionately under the pale glow of streetlights about the nature of reality. They were asking the ultimate questions. Is the universe an objective, enduring home that exists whether we look at it or not? Or is the cosmos a vast, interconnected web of potential, coming into being through the quiet act of awareness? Both men left us a legacy of profound wonder. Einstein gave us a cosmos of magnificent geometric order, where space and time are bound together in a four-dimensional block of absolute harmony. Bohr gave us a subatomic realm of infinite potential, where particles dance in waves of probability, holding the seeds of every possibility. In the physical world around us tonight, both truths exist side by side. The macrocosmos holds its strict, relativistic boundaries. The microcosmos holds its wave functions in silent superposition. The stars burn with deterministic fusion powered by subatomic quantum tunneling. Reality continues its grand, quiet story, preserving its secrets in the deep dark. There are no debates you need to settle tonight, no paradoxes you need to solve, and no choices you need to make. The universe is holding its laws in perfect, unbroken balance. The geometry of spacetime is resting. The quantum fields are quiet. Allow your thoughts to soften. Let the noise of the waking world fall away and drift smoothly into the vast, timeless peace of the sleeping cosmos. Let your body sink deeper into the quiet weight of the night. Feel the gentle, rhythmic rise and fall of your chest as your breath slows, drawing in the cool, still air and releasing every lingering fragment of physical tension. In our previous chapter, we stood witness to the historic debate between Albert Einstein and Niels Bohr, a battle of titans fought over the fundamental nature of reality. We watched as Einstein constructed brilliant thought experiments to defend determinism and local realism, while Bohr defended the probabilistic, observer-dependent realm of the quantum wave function. Yet out of that fierce intellectual rivalry emerged a physical phenomenon so strange, so unsettling, and so deeply counterintuitive that it caused Einstein to recoil in philosophical horror. It was a phenomenon that seemed to threaten the very fabric of his special theory of relativity and the cosmic speed limit of causality. Einstein called it spukhaft-Fernwirkung, a phrase translated into English as spooky action at a distance. Today, we know this phenomenon by its formal scientific name, quantum entanglement. To understand why entanglement shook the foundations of theoretical physics, we must first return to the core principles that Einstein held dear: locality and realism. As we have explored, locality dictates that a physical process happening at one point in space cannot instantaneously affect a physical process happening at another distant point. For influence or information to travel from point A to point B, a signal must travel through the intervening space, and that signal can never exceed the invariant speed of light. See, if a star in the Andromeda galaxy explodes right now, its gravity and light cannot touch Earth until 2.5 million years have passed. The speed of light acts as a cosmic buffer, keeping events isolated and local. Realism, on the other hand, asserts that physical objects possess definite objective properties, such as position, momentum, charge, and spin, regardless of whether anyone is looking at them. A shoe inside a closed box is either a left shoe or a right shoe long before you open the lid to check. Quantum mechanics, through the Copenhagen interpretation, directly challenged realism by asserting that particles do not possess definite properties prior to measurement. They exist as clouds of probability, suspended in superposition. But in 1935, Einstein set out to prove that if you accepted the Copenhagen interpretation, it led to a consequence so absurd that the theory must be incomplete. It demanded that nature violate locality. Einstein, working alongside two young colleagues at the Institute for Advanced Study in Princeton, Boris Podolsky and Nathan Rosen, published a landmark paper that became known as the EPR paper, titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" In this paper, Einstein, Podolsky, and Rosen proposed a thought experiment involving two subatomic particles that become entangled. To understand what quantum entanglement truly means, imagine two subatomic particles, such as two electrons or two photons, created together in a single quantum event. For example, an unstable particle at rest might decay, emitting two identical photons in opposite directions to conserve momentum and angular momentum. Because these two particles were created together from a single source under strict conservation laws, their physical properties are fundamentally linked. They do not possess individual, independent identities. Instead, quantum mechanics describes both particles using a single, unified, indivisible wave function. Psi 12. In classical physics, if two objects interact and fly apart, they each carry away their own definite properties. If you place a red ball and a blue ball into two identical boxes without looking, shuffle them, and ship one box to Tokyo and the other to London, the ball in the Tokyo box is already red or blue the moment it leaves your hands. Opening the box in Tokyo simply reveals a pre-existing fact. Opening the Tokyo box instantly tells you the color of the ball in London, but no physical influence traveled between Tokyo and London. This is simple classical correlation. In quantum mechanics, however, the situation is radically, mind-bendingly different. According to quantum theory, prior to measurement, neither particle possesses a definite physical state. Let us consider a fundamental quantum property known as spin. In subatomic physics, spin is a form of intrinsic angular momentum. For a spin 1-2 particle like an electron, its spin along any chosen spatial axis can be measured as either spin up, plus 1-2, or spin down, minus 1/2. If two entangled electrons are created such that their total combined spin must equal 0 to conserve angular momentum, one electron must be spin up and the other must be spin down. However, under the Copenhagen interpretation, before a measurement is performed, electron A is not spin up, nor is it spin down. It exists in a simultaneous superposition of both states at the exact same time. Simultaneously, electron B also exists in a superposition of both states. The two-particle system is represented by an entangled quantum state. Psi equals 2, 1, up, and down, B, minus down, and up, B. This mathematical equation describes a singular reality. If electron A is measured as spin-up, electron B must be spin-down, and if electron A is measured as spin-down, electron B must be spin-up. But until a measurement occurs, neither electron has chosen its identity. They exist as a shared wave function stretched across space. Now, let us perform the EPR thought experiment across cosmic distances. Imagine creating an entangled pair of electrons in a laboratory on Earth. We keep electron A in a magnetic trap on Earth, while we place electron B inside a protective capsule aboard a high-speed deep space probe and launch it across the intergalactic abyss toward the Andromeda Galaxy, 2.5 million light-years away. For 2.5 million years, the probe glides through the freezing void. Throughout this immense journey, no measurement is made on either electron. Their wave functions remain uncollapsed, delicately entangled across trillions of miles of empty space. Now, an experimenter on Earth approaches the magnetic trap containing electron A and performs a measurement of its spin along the vertical axis. At the exact microsecond the detector clicks on Earth, electron A's wave function collapses. The superposition shatters, and nature rolls its quantum dice. Suppose the detector registers that electron A has collapsed into spin-up. According to the mathematics of quantum mechanics, at that exact, undivided instant, without a single nanosecond of delay, the wave function describing electron B in the Andromeda Galaxy also collapses. Across 2.5 million light-years of space, electron B instantly materializes as spin-down. If an astronaut aboard the Andromeda probe measures electron B one fraction of a second later, they will find it to be spin-down with 100% certainty. This was the core of Einstein's horror. How did electron B, sitting in a distant galaxy 2.5 million light-years away, know that a detector on Earth had just measured electron A? How did electron B know to instantly collapse into spin-down rather than spin-up? If electron B had no definite spin prior to the measurement on Earth, then the act of measuring electron A on Earth must have sent an instantaneous physical signal across 2.5 million light-years to dictate the state of electron B. To Einstein, this was a direct, catastrophic violation of special relativity. Relativity dictated that no signal, no influence, and no information could travel faster than the speed of light, seen across 2.5 million light-years. A signal should require a minimum of 2.5 million years. Yet quantum mechanics predicted that the collapse of the entangled state occurred instantaneously, at infinite speed. Einstein reasoned that there were only two logical possibilities. Either quantum mechanics was wrong, and nature enforced non-local spooky action at a distance, at speeds exceeding light, or quantum mechanics was incomplete, and electron B had been spun down all along, carrying hidden local variables from the moment it left Earth. Einstein was convinced that local hidden variables existed. He argued that quantum mechanics was merely a statistical approximation, like predicting the average roll of a die without knowing the exact mechanical forces acting on it. He insisted that the electron possessed a definite spin from the beginning, hidden from our current instruments, protecting both locality and realism. Niels Bohr, however, held his ground. Bohr argued that there was no spooky signal traveling through space from Earth to Andromeda. Bohr asserted that we must stop thinking of electron A and electron B as two separate physical objects connected by an invisible string across space. In Bohr's view, electron A on Earth and electron B in Andromeda were not two separate objects. They were two manifestations of a single, indivisible quantum system. Distance in the quantum realm was an illusion of macroscopic perception, the two-particle wave function psi. 12 occupied the entire space between Earth and Andromeda as a unified whole. When you measured electron A on Earth, you were not sending a signal to electron B. You were interacting with the entire unified system at once. The collapse of the wave function was not a mechanical process moving through space. It was a non-local reorganization of reality. For decades, this debate remained trapped in the realm of pure philosophy. Both Einstein's local hidden variables theory and Bohr's non-local quantum mechanics yielded the exact same statistical predictions for basic laboratory experiments. There seemed to be no way to test whether Einstein's hidden variables were real or whether Bohr's spooky action was an inescapable truth of nature. Einstein passed away in 1955, believing to his final day that physics would eventually uncover the local, deterministic machinery beneath the quantum veil. Then, in 1964, a quiet Irish physicist working at CERN named John Stuart Bell accomplished what everyone believed was impossible. Bell derived a mathematical theorem, Bell's theorem, that proved that local hidden variables could be experimentally tested and ruled out once and for all. Bell proved mathematically that if Einstein's local realism were true, there was an absolute upper limit to how strongly the measurements of two distant particles could correlate with each other when measured at different angles. This limit was expressed in Bell's inequality. If Einstein was right, the correlation between measurements could never exceed a specific numerical value. If Bohr and quantum mechanics were right, entangled particles would exhibit correlations that breached this barrier, proving that nature is fundamentally non-local. In the late 1970s and early 1980s, a French physicist named Alain Aspect constructed an extraordinarily precise experiment in Orsay, France, using entangled pairs of photons. Aspect used ultra-fast optical switches that could change the angle of measurement while the photons were actively in flight across the laboratory. switching measurement angles in billionths of a second, far faster than any light-speed signal could travel between them. The results of Aspect's experiments, repeated and refined by physics laboratories around the world over subsequent decades, sent a shockwave through the scientific world. Bell's inequality was decisively, indisputably violated. Nature chose quantum mechanics. Nature chose Bauer. Einstein's local hidden variables were proven to be wrong. The universe at its most fundamental level is non-local. Entangled particles do indeed share an instantaneous, non-local connection across arbitrary distances. When the Nobel Prize in Physics was awarded in 2022 to Elaine Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments with entangled photons, it represented the final, formal confirmation of a reality that Einstein found unthinkable. Spooky action at a distance is real. Yet, as we absorb this mind-bending truth, an urgent, vital question arises. Does quantum entanglement break special relativity? Does it allow us to violate the cosmic speed limit c and send messages backward in time? The answer is a subtle, magnificent no. Nature protects its causal order through a profound mathematical safety valve, known as the no-communication theorem. To understand why quantum entanglement cannot be used to transmit messages faster than light, imagine attempting to use our Earth to Andromeda electron pair to send a telegraph signal. Suppose you are on Earth and you want to send a Morse code message to an astronaut in the Andromeda galaxy. You agree in advance that spin-up means 1 and spin-down means 0. You approach your entangled electron A on Earth, intending to collapse its spin into spin-up to instantly force the astronaut's electron B into spin-down. Here is where nature blocks you. You cannot control the outcome of your own measurement. When you measure electron A on Earth, nature's choice between spin-up and spin-down is completely, fundamentally random. You have a 50% chance of measuring spin-up and a 50% chance of measuring spin-down. You cannot force electron A to be spin-up any more than you can force a fair coin to land on heads. The moment you measure electron A, it instantly collapses into a random state, say, spin-up. Across the galaxy, electron B instantly collapses into spin-down. Now, look at the situation from the perspective of the astronaut in Andromeda. The astronaut looks at electron B and measures its spin. They find it to be spin-down. But because the astronaut does not know what result you obtained on Earth, that spin-down result looks to them like a completely random 50-50 quantum event. They have no way of knowing whether electron B collapsed because you measured electron A on Earth, or whether it collapsed simply because they measured it in Andromeda. To the astronaut, their stream of measurements looks like pure, meaningless random noise. Up, down, down, up, down, up. The only way the astronaut can discover the secret correlation, the only way they can confirm that their results are entangled with yours, is if you transmit your list of measurement results to them via a conventional communication channel, such as a radio signal or a laser beam. And that radio signal travels through space at the exact speed of light, c. Entanglement allows instantaneous correlation, but it strictly forbids instantaneous communication. Information, the currency of cause and effect, cannot travel faster than light. The cosmic speed limit holds firm. Relativity and quantum mechanics, despite their deep ideological tension, coexist in a state of peaceful mathematical harmony. Allow your mind to drift across the sheer beauty of this cosmic architecture. Quantum entanglement reveals that the universe is not a collection of isolated, lonely objects scattered across a cold, passive void. Space is not a wall that divides us. Space is a dynamic, quantum medium that holds all of existence in a shared embrace. At the microscopic level, every atom in your body, every photon of light falling upon your skin, and every star shining in the night sky was once compressed together in the hyperdense primordial state of the Big Bang. In those first fleeting fractions of a second, the matter of the cosmos interacted intimately, weaving an intricate, infinite web of quantum entanglements that stretches across 93 billion light-years of space. You are fundamentally connected to the cosmos. You are woven into the non-local fabric of reality. In the quiet dark of this night, as you lie still and untethered from the rush of the waking world, feel the profound peace of being held within this interconnected universe. There are no signals you need to send, no measurements you need to perform, and no paradoxes you need to resolve. The particles in your body are holding their quantum states in quiet, effortless balance. The entangled photons are racing across the cosmic dark, preserving their non-local harmonies. The fundamental fields of nature are maintaining their unbroken, silent unity. Allow your breath to remain slow, deep, and peaceful. Let the boundaries of your thoughts soften, merging into the vast, calm ocean of spacetime. Sleep peacefully, cradled in the profound, interconnected silence of the cosmos. Allow your body to sink fully into the weightless embrace of the dark. Feel the gentle, rhythmic cadence of your breathing, slow, calm, and effortless, as your mind drifts back to the frontier of fundamental physics. In our previous chapter, we explored the eerie phenomenon of quantum entanglement, two subatomic particles sharing a single, indivisible wave function across vast light-years of space. We witnessed how measuring one particle instantly collapses the state of its distant companion, exhibiting a non-local correlation that Einstein famously called spooky action at a distance. Yet this mystery forces us to confront a deeper, even more captivating question, a question that cuts directly to the core of what reality is made of. If physical particles can share instantaneous non-local connections across the cosmos, can information itself be teleported? Can a human being, a signal, or a quantum state vanish from one location in space and instantaneously reappear at another, defying the cosmic speed limit of light? To answer this, we must retrace the brilliant logical architecture of the 1935 landmark paper that started it all. The EPR paradox, authored by Albert Einstein, Boris Podolsky, and Nathan Rosen. When Einstein, Podolsky, and Rosen published their paper titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" They were not attempting to demonstrate that quantum entanglement could be used to build a science fiction teleportation machine. Instead, they designed a rigorous logical trap intended to force quantum mechanics to admit its own incompleteness. The trio began by defining a criterion for what constitutes an element of physical reality. They wrote that if, without in any way disturbing a system, we can predict with certainty, that is, with a probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to that physical quantity. Consider what this means. If you can tell me with absolute 100% certainty what the measurement of a particle will be, without touching or disturbing that particle in any way, then that property must have existed as an objective, physical reality prior to your measurement. Now, recall the scenario of two entangled particles flying apart in opposite directions toward distant corners of the universe. Suppose particle A travels toward an experimenter named Alice on Earth, while particle B travels toward an experimenter named Bob near the edge of the solar system. Because the two particles are entangled, Alice can perform a measurement on particle A on Earth, say, measuring its position or its spin. The moment Alice measures particle A, the wave function collapses, and Alice instantly knows with absolute mathematical certainty what Bob will measure if he checks particle B. Here was the crux of the EPR argument. Alice achieved this absolute certainty about particle B without in any way physically touching or disturbing particle B. Particle B was sitting light hours away, completely isolated in deep space. Therefore, Einstein and his colleagues argued, According to their criterion of reality, the physical property of particle B must have already existed as an objective element of reality before Alice touched particle A. And because quantum mechanics asserted that particle B had no definite property prior to Alice's measurement, Einstein concluded that quantum mechanics was failing to account for these pre-existing elements of reality. The wave function was an incomplete description of nature. There had to be hidden variables, local deterministic parameters, written into the particles at the moment of their creation. For decades, the EPR paper stood as a monument of theoretical challenge. But as we saw through John Bell's theorem and Elaine Aspect's revolutionary experiments, nature ultimately rejected Einstein's local hidden variables. The non-local correlations of quantum entanglement were proven to be real. This led 20th-century physicists to a breathtaking realization. If non-local entanglement is an undeniable feature of our universe, can we use these entangled quantum bridges to perform actual quantum teleportation? In 1993, a team of 6 theoretical physicists led by Charles Bennett of IBM published a paper that turned science fiction into rigorous experimental science. They demonstrated that while you cannot teleport physical matter or transmit faster-than-light messages, you can teleport an unknown quantum state from one location to another. To understand how quantum teleportation works, and why it strictly obeys the cosmic speed limit c, let us construct a thought experiment in our mind. Imagine an experimenter, Alice, who possesses a subatomic particle, a qubit, carrying an unknown, delicate quantum state. We will call this target particle X. The state of particle X contains specific quantum information, a precise superposition of spin-up and spin-down. Alice does not know the exact state of particle X, and under the laws of quantum mechanics, if she tries to measure it directly, her measurement will collapse the wave function, destroying the very information she wants to transmit. Alice wishes to transport this fragile, unknown quantum state of particle X to her colleague Bob, who is stationed at a distant space station, light years away. How can Alice send this information to Bob without destroying it, and without physically launching the particle across the void? This is where the magic of quantum teleportation unfolds, relying on 3 essential components. First, an entangled pair of particles, particle A and particle B, is created in a laboratory. Particle A is delivered to Alice, while particle B is delivered to Bob. They now share a non-local quantum bridge stretching across light years. Second, Alice takes her unknown target particle, particle X, and brings it into physical contact with her half of the entangled pair, particle A. Alice does not measure particle X or particle A individually. Instead, she performs a specialized joint quantum measurement on both particles simultaneously, a procedure known as a Bell state measurement. When Alice performs this Bell state measurement, something extraordinary happens. The measurement forces particle X and particle A to entangle with each other. But in doing so, the original, delicate quantum state of particle X is completely erased from particle X. The original information vanishes from Alice's laboratory. Simultaneously, because particle A was entangled with Bob's distant particle B, Alice's joint measurement causes the quantum wave function of Bob's particle B to instantly react. The state of Bob's particle B is altered across light years. However, Bob's particle B does not instantly become an exact replica of the original particle X. Instead, Bob's particle is left in a state that is mathematically rotated or modified relative to the original state. This brings us to the third and most crucial step of the protocol, the classical channel. When Alice performed her Bell state measurement on particles X and A, her measurement produced a random result, one of 4 possible outcomes. Alice must now take those 2 bits of classical information, representing which of the 4 outcomes occurred, and send them to Bob. How does Alice send those two bits of information to Bob? She must send them using a conventional classical signal, a radio pulse, a laser beam, or a fiber optic transmission. And that classical signal travels through space at the exact speed of light, c. Until Bob receives those two classical bits from Alice, his particle B is in a scrambled, completely unreadable state. It looks like pure, meaningless quantum noise. Bob cannot extract any information from particle B. He does not know how to orient his instruments. The instant the laser signal carrying Alice's two classical bits arrives at Bob's space station, traveling at speed c, Bob reads the two bits. Depending on whether Alice's result was 0, 1, 10, or 11, Bob applies a specific mathematical rotation to his particle B using a magnetic field or a laser pulse. The moment Bob applies that simple rotation, particle B instantly transforms into an exact, perfect replica of the original quantum state of particle X. The quantum state has been teleported. The delicate information carried by particle X vanished from Alice's lab on Earth and materialized in Bob's particle light years away. Yet examine the profound physics governing this feat. Was information transmitted faster than light? No. Even though the entangled bridge reacted instantaneously, Bob could not reconstruct or read the teleported state until Alice's classical lightspeed signal arrived at his doorstep. If Bob attempted to guess the state before receiving Alice's message, he would be wrong 50% of the time, obtaining nothing but random noise. The classical speed of light c acted as an absolute bottleneck, keeping the transmission of information strictly bounded by causality. Was the original particle copied or cloned? No. In classical computing, you can effortlessly make infinite copies of a digital file. You can copy a string of ones and zeros, leaving the original file intact while sending a duplicate across the internet. In quantum mechanics, however, nature enforces an unbreakable law discovered in 1982 by physicists William Wouters, Wojciech and Dennis Dieks, the no-cloning theorem. The no-cloning theorem proves mathematically that it is impossible to create an identical copy of an arbitrary, unknown quantum state without destroying the original state. During the quantum teleportation protocol, the moment the state materialized in Bob's particle B, the original state of particle X in Alice's lab was completely destroyed by her Bell state measurement. The information was not duplicated. It was transferred. The universe strictly forbids the existence of two identical, independent copies of an unknown quantum state. Quantum teleportation is not science fiction matter displacement. It is the transfer of pure quantum information across an entangled space bridge, governed perfectly by the speed of light and the laws of causality. Today, quantum teleportation is no longer merely a theoretical thought experiment. In laboratories around the world, scientists routinely teleport the quantum states of photons, atoms, and complex ions across tens of kilometers of fiber optic cables, and even through open space. In 2017, Chinese scientists achieved quantum teleportation between a ground station in Tibet and a satellite orbiting 1,400 kilometers above the Earth, laying the physical foundations for a future quantum internet. This deep relationship between quantum mechanics, entanglement, and teleportation has forced modern physics to embrace a radical new perspective on the nature of reality itself. For centuries, science viewed the universe as being built primarily out of matter and energy. Space was the container, atoms were the building blocks, and energy was the currency that moved them. In the late 20th century, the legendary theoretical physicist John Archibald Wheeler proposed that we must add a third, even more fundamental pillar to our understanding of the cosmos: information. Wheeler coined the famous phrase, "it from bit." Wheeler suggested that every physical particle, every gravitational field, every star, and every fabric of spacetime, derives its very existence from binary choices, from quantum bits of information embedded in the source code of nature. Physical reality is not made of tiny, hard billiard balls. Physical reality is an information processing architecture. When you look at a subatomic particle, you are not looking at a solid speck of dust. You are looking at a localized bundle of quantum information: mass, charge, spin, position, and momentum. Quantum entanglement reveals that information is not merely a human concept written in books or stored on hard drives. Information is a fundamental physical property of spacetime. It can be shared non-locally across light years, encoded onto event horizons, and transferred through quantum channels, all while preserving the strict, logical order of cause and effect. As you lie here in the quiet sanctuary of the night, allow this profound truth to bring peace to your awareness. Think of the vast, silent information network woven across the cosmos. Trillions of subatomic particles in your body are interacting with the environment, holding their quantum states in exquisite, stable balance. The light traveling from distant galaxies carries ancient quantum information across the light years, bounded safely by the invariant speed c. The universe is logically consistent, infinitely rich, and deeply protected. No signal can outrun its cause. No information can break the tempo of spacetime. No quantum state can be lost or cloned into chaos. There are no codes you need to decipher tonight, no signals you need to send, and no states you need to measure. The quantum fields are holding their information in perfect, silent harmony. The non-local bridges are resting. The fabric of reality is secure. Feel the slow, rhythmic comfort of your breath. Let your thoughts soften, merging into the vast, calm, information-rich ocean of the cosmos. Sleep peacefully, cradled in the timeless, orderly silence of the universe. Allow your body to rest completely in the soft, weightless calm of the dark. Breathe slowly and deeply, letting the peaceful rhythm of your lungs wash away every remaining thought of the waking world. In our journey so far, we have explored the deep ideological rift between Albert Einstein and Niels Bohr, a clash between Einstein's local realism, where objects have definite properties and signals cannot outrun light, and Bohr's quantum world, where properties remain undetermined until measured. For nearly 30 years, this debate was treated as a matter of philosophy rather than experimental science. Physicists assumed it was impossible to test whether an entangled particle carried hidden local variables, or whether nature truly operated on non-local quantum correlations. That was until a quiet Irish physicist working at CERN, named John Stuart Bell, devised a mathematical theorem that transformed this philosophical dispute into an experimental reality. John Bell was a practical accelerator physicist who spent his days calculating the trajectories of high-energy particle beams. But in his quiet evenings, he was captivated by the foundational paradoxes of quantum mechanics. Bell admired Einstein's commitment to local realism, but he wanted to see if Einstein's local hidden variables could ever be put to a rigorous mathematical test. In 1964, Bell published a paper that changed physics forever, on the Einstein-Podolsky-Rosen paradox. In this paper, Bell constructed a mathematical formulation, now known as Bell's inequality, that laid down an absolute physical limit. He proved that if Einstein was right, if physical particles possess local hidden variables determined at the moment of their creation, then there is a strict upper bound on how strongly two distant particles can correlate with each other when measured along different angles. To understand the genius of Bell's theorem without complex equations, let us picture a simple thought experiment. Imagine two experimenters, Alice and Bob, stationed at opposite ends of a large laboratory. In the center of the room sits a source that repeatedly creates pairs of entangled photons and sends one photon to Alice and one to Bob. Alice and Bob each possess a polarizing filter that can be rotated to different angles, for instance, 0, 45, or 90. When a photon encounters a filter, it either passes through, which we record as +1, or gets blocked, which we record as -1. If Einstein's local realism is correct, each photon leaves the source carrying a set of hidden instructions, an internal code that predetermines whether it will pass or fail at any possible filter angle. The photons are like two identical twins leaving a house, each wearing matching outfits hidden under their coats. No matter which angle Alice and Bob choose to measure, the outcome was written into the photons before they ever left the source. Bell calculated the mathematical probability of Alice and Bob getting matching results when they randomly rotated their filters to different angles. Under any local hidden variable theory, where information travels no faster than light and properties exist prior to measurement, the statistical correlation between Alice's and Bob's measurements cannot exceed a specific numerical value. This is the core of Bell's inequality. However, when Bell used the standard equations of quantum mechanics, where particles have no definite properties prior to measurement and share an indivisible wave function, he discovered something astonishing. Quantum mechanics predicted that, for certain filter angles, the correlation between the two photons would violate Bell's inequality. The quantum correlations were mathematically stronger than anything permitted by local realism. Bell had created a clear binary test. If laboratory experiments obey Bell's inequality, Einstein is right. Local realism is preserved, and quantum mechanics is incomplete. If laboratory experiments violate Bell's inequality, Bohr is right. Local realism is dead, and the universe is fundamentally non-local. In the late 1970s and early 1980s, a French physicist named Alain Aspect set out to build the definitive experiment at the Institut d'Optique in Orsay, France. Aspect and his team designed an extraordinary apparatus using calcium atoms to generate pairs of entangled photons. But Aspect knew he had to close a critical loophole that Einstein's defenders might use, the locality loophole. What if the two detectors were somehow communicating with each other during the experiment? What if a sublight signal passed between Alice's detector and Bob's detector, telling them which filter angle was selected? To close this loophole, Aspect designed high-speed optical switches that could change the orientation of the polarizing filters, while the photons were actively in flight through the air. The photons traveled across the room at the speed of light, taking merely 20 nanoseconds to reach the detectors. Aspect switches rotated the filter angles every 10 nanoseconds. Because the filter angles were chosen randomly while the photons were already in midair, no physical signal, not even a signal traveling at the speed of light, c, had enough time to travel from Alice's detector to Bob's detector before the measurement was completed. The two measurements were strictly separated in spacetime. The results of Alain Aspect's 1982 experiment were decisive. The experimental data violated Bell's inequality with overwhelming statistical certainty. The photons correlated with each other precisely as predicted by quantum mechanics. The correlations were stronger than any local hidden variable theory could ever allow. In the decades that followed, physicists around the world constructed increasingly elaborate, loophole-free Bell tests. They separated entangled particles across miles of fiber optic cables under cities, bounced entangled photons off satellites in space, and even used light from ancient quasars billions of light-years away to choose detector angles randomly. Every single test delivered the same verdict: Bell's inequality is violated. Alain Aspect, John Clauser, and Anton Zeilinger were awarded the 2022 Nobel Prize in Physics for these monumental experiments. The philosophical impact of Bell's theorem is staggering. It forced humanity to abandon one of its most cherished assumptions about nature. Einstein believed in local realism, the idea that the universe is both local, no faster-than-light signals, and real objects have definite properties independent of observation. Bell's theorem, combined with Aspect's experiments, proved that our universe cannot be both local and real. We are forced to make a profound choice. Either we give up locality. Physical events can be instantaneously linked across space without physical signals traveling between them. Or we give up realism. Physical properties do not exist until they are measured. Most modern physicists accept that nature has chosen to abandon local realism. Space is not a rigid barrier that isolates events into independent boxes. Beneath the classical surface of spacetime lies an interconnected quantum foundation where non-local correlations hold reality together. Yet remember the great cosmic balance we explored in Chapter 5. Nature enforces the no-communication theorem. Even though entangled particles exhibit non-local correlations that violate Bell's inequality, this connection cannot be used to transmit a controllable, faster-than-light signal. The individual outcome of every measurement remains completely random. You cannot force a particle to collapse into a specific state to send a Morse code message to a distant star. Cause and effect remain safely protected by the speed of light, c. As you float here in the deep, quiet sanctuary of the night, absorb the serene grandeur of this realization. The experiments of Bell and Aspect did not reveal a chaotic or broken universe. They revealed a cosmos far more unified and deeply woven than classical physics ever dared to dream. The universe is not a collection of isolated, cold objects drifting in an empty void. It is a single, interconnected tapestry where space holds everything in a shared quantum embrace. Your body, your breath, and the air around you are part of this grand architecture. The atoms within you are bound by the same quantum field equations that govern the stars. Everything is held in exquisite mathematical harmony. There are no loopholes you need to close tonight, no inequalities you need to test, and no correlations you need to measure. The physical laws have tested reality, and reality has proven to be an unbroken, unified whole. Feel the slow, calming rhythm of your breath. Let your thoughts settle, let your body relax completely, and drift peacefully into the deep, timeless, interconnected quiet of the universe. Allow your body to sink deeper into the stillness of the night, letting the rhythmic, effortless flow of your breathing anchor you in absolute calm. In our exploration of quantum mechanics and Bell's theorem, we confronted a reality that unsettled even the greatest minds in history. The subatomic world is genuinely non-local. Entangled particles share an instantaneous, invisible connection that transcends distance, defying the classical rules of separation. This undeniable truth brings us face to face with the most profound tension in modern physics. If quantum entanglement allows particles to correlate instantaneously across trillions of miles, doesn't it completely shatter Albert Einstein's special relativity? Doesn't it mean that information can travel faster than the cosmic speed limit of light, tearing down the barrier between cause and effect? To resolve this profound paradox, we must look closely at what it means to communicate and how the universe protects its own logical consistency through a masterwork of mathematical design known as the no-communication theorem. At first glance, the temptation to view entanglement as a faster-than-light telegraph is irresistible. Imagine standing on Earth with one half of an entangled pair of electrons, while your colleague holds the other half near the edge of a distant galaxy. If measuring your electron instantly forces its distant companion into a specific state, it feels as though you have pulled a cosmic lever that reacts at the other end of the universe with zero delay. Yet a vital, unyielding law of quantum mechanics stands directly in the path of this sci-fi dream: the absolute randomness of quantum measurement. When you approach your electron on Earth to measure its spin along a chosen axis, you cannot choose or control the outcome. Nature does not present you with a predictable sequence of ones and zeros. Instead, the wave function collapses randomly, giving you a 50% chance of measuring spin-up and a 50% chance of measuring spin down. You have no more control over the result of a quantum measurement than you do over the flip of a fair coin. Now, consider what your colleague sees across the galaxy when they measure their entangled electron. Because your measurement yielded a completely random result, your colleague's corresponding measurement will also yield a completely random result. When they look down at their detector, they see a string of outcomes: up, down, down, up, down. To them, this stream of data looks like pure, meaningless, random noise. They have no way of knowing whether their particle collapsed because you performed a measurement on Earth, or whether it simply collapsed because they measured it locally in their own laboratory. To extract any meaningful message from those results, to discover the secret correlations shared between your particles, you must compare your notes with your colleague. You must tell them what angles you used and what results you obtained. And how do you transmit those notes across space? You must send them using a conventional classical channel, a radio wave, a laser pulse, or a fiber optic cable. And that classical signal must travel through space at or below the invariant speed of light, c. The instantaneous correlation of entanglement is entirely real, but it remains utterly blind and uncontrollable. You can correlate data instantly, but you cannot transmit a deliberate message faster than light. The cosmic speed limit holds firm, safeguarding the sequence of cause and effect across the universe. This delicate separation between correlation and communication protects the universe from temporal paradoxes. In physics, if you could send a signal faster than light, you could create scenarios where an effect arrives at its destination before the cause ever occurred. You could send a message into your own past, creating loops where events undo themselves, unraveling the logical fabric of reality. The universe prevents these paradoxes through the exquisite mathematical architecture of quantum mechanics. Entanglement provides a non-local bond, but nature ensures that this bond remains hidden behind a veil of pure quantum randomness until a classical, light-speed messenger arrives to unlock it. As you lie here in the quiet sanctuary of the night, absorb the peaceful harmony of this realization. Special relativity and quantum mechanics, the two great pillars of modern physics that once seemed locked in mortal combat, coexist in a state of profound, elegant balance. Relativity provides the macro-scale stage, keeping space structured, causality protected, and light moving at a disciplined, constant tempo. Quantum mechanics provides the micro-scale foundation, weaving particles together in a shared, non-local embrace without ever breaking the rules of the macro world. The cosmos is neither chaotic nor fragile. It is deeply ordered, logically secure, and bound together by laws of breathtaking beauty. There are no paradoxes you need to resolve tonight, no signals you need to intercept, and no faster-than-light velocities you need to calculate. The quantum fields are holding their harmonies in silent equilibrium. The speed of light is guarding the boundaries of space. Everything is resting in absolute peace. Feel the slow, rhythmic comfort of your breath. Let your thoughts soften, merging into the vast, calm ocean of the universe. Sleep peacefully, cradled in the orderly, timeless silence of the cosmos. Allow your body to sink deeper into the quiet weight of the night, letting the steady, rhythmic rise and fall of your breath anchor you in total calm. In our exploration of the cosmos, we have repeatedly returned to the absolute speed limit of reality, the invariant constant c, 300,000 kilometers per second, the strict master tempo that governs causality and prevents physical objects or information from racing ahead of their own origins. Yet, as we lift our gaze from individual particles to the grandest architecture of the universe itself, we encounter a breathtaking paradox that seems to challenge this limit entirely. We discover that space itself can expand, stretch, and carry distant galaxies away from us at speeds vastly faster than light, without ever breaking a single law of physics. To understand how the universe can outrun its own light, We must journey into the smooth, dynamic geometry of general relativity and witness the quiet expansion of the cosmos. When astronomers in the early 20th century first turned their telescopes toward distant nebulae, they expected to find a static, eternal universe, a steady, unchanging cathedral of stars resting in a permanent void. But through the pioneering observations of Edwin Hubble, a startling revelation emerged. By analyzing the light spectrum of distant galaxies, Hubble discovered a phenomenon known as redshift. The characteristic spectral lines of hydrogen and other elements in distant galaxies were shifted toward the red end of the spectrum, indicating that they were moving away from us. And more remarkably, the further away a galaxy was located, the faster it was receding into the dark. Galaxies twice as distant were moving away twice as fast. Galaxies 10 times as distant were rushing away 10 times as fast. The universe was not static, it was expanding. At first glance, this discovery caused deep confusion among physicists. If distant galaxies are rushing away from us at velocities that, at immense distances, exceed the speed of light, how does this not violate Einstein's special relativity? How can celestial objects outrun light if nothing can travel faster than c? The resolution to this profound puzzle lies in a vital distinction between moving through space and space itself expanding. Special relativity governs objects moving through the static fabric of spacetime. A rocket ship, an electron, or a beam of light traveling across a room is bound by the local speed limit of c. Nothing with mass can accelerate past this boundary, and no signal can outpace light through the vacuum. But general relativity reveals that the fabric of space itself is not a rigid, passive backdrop. Spacetime is elastic, dynamic, and capable of stretching. Imagine drawing two dots on the surface of an uninflated rubber balloon, representing two distant galaxies. As you slowly blow air into the balloon, the rubber stretches, and the space between the two dots expands. The dots move further apart from each other not because they are actively swimming across the rubber surface under their own power, but because the very medium of space beneath them is expanding. As more space is created between them, the distance grows. The galaxies themselves are nearly at rest relative to their immediate local neighborhood. It is the expanding fabric of the cosmos between them that is stretching. Because space is not a physical object possessing mass, it is not bound by the speed limit of special relativity. There is no physical law restricting how fast the geometry of space can stretch. The metric expansion of the universe can proceed at any rate, carrying distant galaxies outward at velocities that surpass 300,000 kilometers per second, and eventually exceeding the speed of light. This means there are regions of the universe, at the extreme edges of the observable cosmos, that are receding from us faster than light. The light emitted by stars in those distant galaxies is racing toward us at c, but the space through which that light must travel is expanding away from us even faster, like a runner trying to sprint forward on a treadmill that is accelerating backward at a higher speed. As a result, the light from those distant regions will never reach us. It is trapped beyond a boundary known as the cosmological event horizon, a quiet, invisible edge marking the limit of everything we can ever see, measure, or know in this universe. Beyond that horizon lies a vast expanse of space continuing to expand in absolute silence, forever hidden from our view. Yet, despite this cosmic stretching, the local space around you remains calm, stable, and firmly bound. The expansion of the universe does not tear apart atoms, nor does it pull apart the planets in our solar system, or stretch the structure of the Milky Way galaxy. Local gravitational forces, the mutual attraction between masses, are infinitely stronger than the feeble expansive pressure of dark energy operating on small scales. The Earth remains anchored to the Sun, the stars remain locked in their galactic orbits, and the air you breathe stays resting gently against the surface of our world, held in place by local gravity. The stretching of space only manifests across vast, intergalactic distances, operating silently across millions of light-years of void. As you lie here in the quiet sanctuary of the night, Absorb the serene magnitude of this reality. The universe is not a rigid box. It is a living, expanding tapestry, stretching outward into the infinite dark in profound, unhurried harmony. The galaxies are drifting away along the curves of expanding space, carrying the history of the cosmos into distant horizons, while local gravity holds our home safe in steady, quiet balance. There are no expanding horizons you need to measure tonight, no receding galaxies you need to chase, and no cosmic speeds you need to calculate. The fabric of space is holding its geometry in quiet, effortless equilibrium. The expansion is gentle, the boundaries are secure, and everything is resting in absolute peace. Feel the slow, rhythmic comfort of your breath. Let your thoughts soften, merging into the vast, calm ocean of the expanding cosmos. Sleep peacefully, cradled in the timeless, orderly silence of the universe. Allow your body to sink fully into the soft, weightless calm of the dark. Breathe slowly and deeply, letting the peaceful rhythm of your lungs wash away every remaining thought of the waking world. As we reach the final horizon of our journey tonight, let us gather together the magnificent threads of the cosmos we have explored, from the strict, disciplined tempo of the speed of light to the ghostly, non-local embrace of quantum entanglement and the vast, stretching oceans of expanding space. Throughout this exploration, we have witnessed a universe built upon two seemingly contradictory pillars. On one grand scale, Albert Einstein revealed a cosmos of breathtaking geometric harmony. Space and time are woven together into a four-dimensional tapestry where the speed of light, c, stands as an absolute guardian. It is the master gear ratio of causality, protecting the sequence of events, ensuring that cause always precedes effect, and keeping the macro world orderly, predictable, and secure. Yet when we zoom down into the microscopic heart of that very same universe, the rules transform. In the subatomic realm of quantum mechanics, particles dance as clouds of probability, wave functions stretch across the void, and entangled pairs share an instantaneous, non-local connection that defies distance. Across light-years of space, particles whisper to one another in an unbroken unity, proving that the universe at its foundation is deeply, profoundly interconnected. And across the vast intergalactic expanses, the fabric of space itself stretches outward, carrying distant galaxies away faster than light, opening up horizons that expand into the infinite silence of the night. These two worlds, the strict relativistic stage and the fluid quantum web, do not conflict. They coexist in a state of exquisite, peaceful balance. Relativity keeps the macrocosmos stable, ensuring that information remains bounded, causality is preserved, and human life can unfold beneath a steady, dependable sky. Quantum mechanics binds the atomic architecture together, powering the stars, holding our physical form in stable standing waves, and weaving every particle into a shared, universal fabric. When we look up at the night sky from a quiet place on Earth, we are not looking at a cold, fragmented collection of isolated rocks and lonely stars. We are gazing into an integrated living tapestry where everything is linked by gravity, light, and quantum information. The light from ancient suns travels across the light years to reach our eyes, carrying messages from the deep past. The atoms in your body were forged in the hearts of dying stars and bound together by quantum fields that span the cosmos. You are not separate from the universe. You are an expression of it. The consciousness that allows you to wonder about the stars, to question the speed of light, and to seek peace in the quiet dark is the universe waking up and observing itself. There are no more equations to solve tonight, no paradoxes to untangle, and no boundaries to cross. The cosmic speed limit is guarding the edges of space. The quantum fields are holding their harmonies in silent equilibrium, and the expanding universe is stretching outward in gentle, unhurried grace. Let the last remnants of the day dissolve into the quiet dark. Feel the slow, effortless comfort of your breath. Let your thoughts soften, merging completely into the vast, calm, and timeless ocean of the cosmos. Sleep peacefully, cradled in the orderly, eternal silence of the universe.